دوستان عزیز ارجمند، کانون مهندس امروز افتخار بزرگی داره که میزبان فرزانه دانشمندی است که شهرت و شخصیت علمی جهانی است. پروفسور نادر انقطاع امروز مهمان کانون مهندس است. ای کاش خود نادر حضور نداشت که من می توانستم در سجایا و شایستگی اخلاقی ایشون صحبت کنم. مقام علمی ایشون که بر همه جهانیان آشکار هست و احتیاج به توصیف من نداره. انسانی متواضع، صمیمی، از خود گذشته، با محبتی از جان برخاسته. برای این کسانی که میخوان به صدق گفتار من پی ببرن، به خاطرات برادر فقید ایشون دکتر ناصر انقطاع، شخصیت فرهنگی و برجسته میهن ما، کافیست مراجعه کنن تا متوجه بشن که چقدر این شایستگی به حق هست. به هر حال من اجازه میخوام که از آقای مهندس افشین خدابنده درخواست کنم که رزومه ایشون رو در اختیار من مختصری برای ما بگن تا ما آرام آرام شروع کنیم به کار. من و آقای مهندس فروزی و آقای مهندس بهشاد صباح کار پشتیبانی برنامه رو عهده داریم و در خدمت دوستان هستیم. ایشون و میکروفون در اختیارشون هست و افشین جان بفرمایید.
درود بر همه دوستان. وظیفه به عهده من گذاشته شده که این وظیفه آسانی نیست، این مسئولیت کمی نیست. من باید رزومه 190 صفحه‌ای ایشون رو اینجا خلاصه بگم که ایشان واقعا در هر زمینه‌ای فعالیت چشمگیری داشتن و از ابتدا بخوام شروع کنم، ایشان دبیرستان هدف، من افتخار داشتم که ایشون هم مدرسه ما بود، بعد ایشان دانشکده فنی لیسانس مهندسی برق گرفتن، بعد تشریف بردن به کالیفرنیا کلتک، اونجا فوق لیسانس و دکترا گرفتن و بعد از اینکه دکترا گرفتن، بعد از 1-2 سال به دانشگاه پنسیلوانیا تشریف بردن و اونجا مشغول تدریس و تحقیق و کارهای علمی شدن. و آقای دکتر انقطاع نه تنها در زمینه‌های علمی بسیار فعال هستند و دارای اختراعات و اینویشن های زیادی هستند، ایشان بسیار سختگوش و پرکار هستند و ایشان مثلا من بخوام چند رشته رو بگم، ایشان در الکتریکال اند سیستمز انجینیرینگ کار میکنن، در زمینه فیزیکس و استرونومی کار میکنن، در زمینه بیو انجینیرینگ کار میکنن، در زمینه نیر زیرو ایندکس متریالز کار میکنن و به طور کلی متریال ساینس، و در زمینه نانو، در نانوگرافینز و نانو اپتیکس و گرافین فوتونیکس و مایکروویوز و الکترودینامیکس و زمینه های دیگری کار میکنن. و حتی ایشان گاهی سری هم به دانشکده های دیگه مثل بیولوژی و اینها هم زدن و کارهایی هم مشترکاً انجام دادن که شاید در پرزنتیشن امروزشون به اون اشاره بکنن. و ایشان جوایز بسیاری دریافت کردن که آخرین جایزش رو همین چند ماه قبل جایزه بنجامین فرانکلین رو، در واقع مدال بنجامین فرانکلین رو گرفتن که این جایزه بسیار مهم و پرپرستیژی هست که هر ساله داده نمیشه. فقط وقتی این جایزه رو میدن که شخصی صلاحیت و شایستگی شو داشته باشه. ایشان بیش از 370 مقاله علمی خودشون یا مشترکاً منتشر کردن، در 350 مرکز علمی تحقیقاتی دنیا سخنرانی کردن، حدود 30 تا اختراع ثبت شده یا در شرف ثبت دارن و بیش از 50,000 بار به مطالب علمی ایشون ارجاع شده در کارهای علمی. و من بخوام ادامه بدم تا همه این 2 ساعت باید در مورد ایشون صحبت کنم. فقط همینقدر بگم که در بعضی از نشریات و مجلات علمی که من گاهی ورق زدم برخورد کردم به همکاران ایشون که اونها هم صاحب نظر هستند در همین علوم فیزیک و الکترونیک و اونها مستقلاً ایشان رو شایستگی یک کاندیدای شایسته‌ای برای جایزه نوبل دونستن. من امیدوارم که به زودی ما بتوانیم جشن باشکوهی اختصاصاً برای دریافت جایزه نوبل از طرف ایشان داشته باشیم و من دیگه همینجا عرایزم رو قطع میکنم، نه به دلیل اینکه آقای پروفسور انقطاع مطالبشون گفته شد، بلکه دیگه واقعا نمیخوام زیاد وقت بگیرم. همه ما در اختیار بیانات ایشون هستیم. آقای دکتر بفرمایید.
سلام و درود به همه دوستان در اینجا و اول از همه میخوام از دوست عزیزم افشین جان تشکر بکنم و همچنین آقای مهندس محقق برای دعوت شما به کانون مهندسین. واقعا برای من افتخاری هست که با شما باشم و در جمع دوستان باشیم و با هم صحبت بکنیم در مورد یکی از رشته‌هایی که افشین جان گفتن هم شب با هم صحبت بکنیم. خیلی سپاسگزارم از افشین دوست عزیزم که با محبت و خیلی سخاوتمندانه در مورد من صحبت کردن و همچنین از تمام دوستان شما ممنون هستم که امشب وقتتون رو گذاشتین که با هم صحبتی بکنیم. فقط می‌خواستم یک نکته کوچیکی رو تصحیح بکنم در کلماتی که افشین عزیز گفتن و اینکه جایزه بنجامین فرانکلین مدال هر سال داده میشه. از سال 1824 شروع شده و هر ساله داده میشه. در نتیجه فقط این مسئله کوچیک رو مثلا تصحیح بکنم در جمله‌ای که افشین جان گفتن. خب اگه اجازه بدین من این پرزنتیشن رو شیر بکنم. این اسلاید منو میبینین کاملا؟ افشین جان همونجوری که من گفتی اگه اشکال نداشته باشه من یه مقدار از این سخنرانی رو به انگلیسی بگم. اگر
بله اتفاقا ما اینجا آمادگی داریم که شما اگر مایل هستید کل سخنرانیتون رو به انگلیسی هم میتونید بگید، ولی به هر میزان که راحت هستید انگلیسی فارسی ما در خدمتتون هستیم.
من سعی میکنم هر دوشو بگم، ولی بعضی از لغات البته خب به انگلیسیش راحت‌تر گفته میشه، ولی سعی میکنم که هر جور که راحت بشه. از همه تقاضا میکنم اگه هر موقعی سوالی داشته میتونید منو متوقف بکنیم و با هم صحبت بکنیم. یه پرزنتیشن اینفورمالی هست که میتونیم با هم داشته باشیم. همونطور که تایتل سخنرانیم گفته میشه I want to talk about using the polarization of light to image and to see things that ordinarily we would not see. That's what I put the title, Seeing the Unseen, Imaging with Light's Polarization. Now, قبل از اینکه وارد این مسئله بشیم, if you remember from my previous presentation, I mentioned that, one of the areas of my interest is physics and engineering of waves. What we can do with waves, how do we control the waves, how do we manipulate the waves in order to do interesting functionalities. And I actually, in that presentation, I showed, 2-3 slides about this topic as well, but also I talked about other things. So tonight, I'm going to go a little bit deeper into this topic and really see, some of the interesting features that polarization of light can provide to us. And I'm going to explain what these are. But before I get into the, technical aspect of the talk, I want to tell you an interesting story. And how I got interested actually in this field of research. As you will see in the first part of my talk, I'm going to talk about the biology of visual system. Now, I'm not a biologist at all, but accidentally I got into the field of biology and polarization vision. And I want to tell you the story of how that actually happened. Often in science and technology, sometimes accidentally you get into interesting fields and which you didn't plan before, and then you pursue that and you get some interesting, outcome. So few years after I came to University of Pennsylvania, I was young at that time, and one day in my office, I got a phone call from a professor from the Department of Psychology. Now, the name of that professor is Professor Ed Pugh. I didn't know him. I had heard about his name, and he's a very famous and senior professor, and I was a young assistant, at that time, associate professor. And he told me that he would like to talk to me because he has some interesting technical questions he would like to ask me regarding the optical fibers. Now, I was very intrigued. This why someone in Department of Psychology is interested with optical fibers. That's number one. Number two, he was a very famous professor. He's still a very famous professor, and I was just a young, associate professor. How does he need to talk to me? Anyway, I was very curious and I was very intrigued. So we made an appointment, and I went to his office. And I went to his office. He showed me this picture. Now, if I was giving this talk, in front of the audience, in front of all of you, I would ask this question: what do you think this is? This is a picture of what that you are seeing on the screen?
Crystal?
Crystal? No, it's not crystal. It does look like crystal, but it's not.
How about the nervous system on the
You're getting close to that, but it's not a nervous system. So let me
Eyes of an insect?
Exactly right. This is the cross-section of the retina of a class of fish known as green sunfish, or technical term for that fish is Lopomus cynellus. Now, this is the cross-section that this friend of mine, and later on became very good friend and collaborator, Professor Ed Pugh, had gotten from this special fish. And what you see over here is basically those photoreceptor cells in the retina of this species. So, for example, this circular cross-section that you see over here is the cross-section of the cone photoreceptors. And but also there's some interesting things in this structure that you see. It looks like two cells are being fused together. And in this, they call it the double cone photoreceptors that you see over here. And so he told me that the reason he wanted to talk to me because there's some evidence that this fish can see polarization of light. And he had some hypotheses about why and how this fish would see polarization of light. So I was very intrigued. Now, at that time, I was familiar, with the radar system. I was familiar with antenna system. And I know, how the polarization of electromagnetic wave behaves. But I didn't know anything about how in nature, some of the species can also see polarization of light. And I'm going to explain that a little bit more. But before I go, let me show you, by the way, these two pictures that you see over here. This is the scanning electron microscope of that cell that you see over here. You see, it just like two cones are being fused together. And this is basically the sketch of that cell that you see over here. By the way, do you see the cursor of my computer? So you can see the picture I show. So you see, just to give you an idea, by the way, this is about 14 microns. So this dimension is about 14 microns. Just to give you an idea of the dimension, if we get one strand of our hair, the thickness of our hair is 100 microns. So this is roughly about, 1/10, even more than that, of the thickness of the hair that you see there. And the length of it is about 30 microns. And so I was really fascinated by this story that he told me, that in nature, there are some animal species that can see polarization of light. So, by the way, let me show you this fish. So this is a very interesting fish. It's about, a few inches tall, and they're actually quite vicious. If they want to keep them in the tank of water, they have to separate them, otherwise they fight with each other. And by the way, this colleague of mine, Professor Edward Pugh, was at the University of Pennsylvania at that time when I met him for the first time, but he later moved to University of California, Davis, and he's currently a professor there in the Department of Ophthalmology. Now, so what is polarization? How does this species actually see polarization of light? And what can we do with it? What interesting feature we can do with that? So let me take you to the physics of waves. I briefly talk about this, by the way, in my first talk that we talked together last time that we had this meeting. So if you look at an optical wave, optical waves has several properties. One is the intensity of the wave. In other words, how strong is the field. And another one is the wavelength of the wave. And the wavelength is essentially the distance between two peaks of this wave that you see over there. But electromagnetic and optical waves has another property, and that is the polarization of the wave. And what is the polarization? In Farsi, میگیم قطبی شدن of the wave. به این صورت هست که تصور کنید که شما، حالا من به مثال مکانیک یا مثال فیزیکی براش میزنم. تصور کنید شما یه سیم داشته باشین و این سیم رو همینطور بالا پایین ببرین. وقتی یه سیم رو یا طنابی رو بالا پایین ببرین، you notice that there is a wave there. But the direction of motion that you have, you're taking up and down, creates a wave that goes up and down. But if you get that سیم رو شما بگیرین and you move it left and right, you also create a wave, but that wave goes back and forth. So that is the direction of this vibration that you have is called polarization. And in the case of optical and electromagnetic wave, that vibration is a vibration of electric field of that wave. Now, so this is, of course, very well known in electromagnetic wave propagation. And but how does this actually enter into the field of biology and into the field of particularly the visual system of all of us and also in other species in nature? So human eye is an amazing part of the anatomy that we have. It's an amazing detector. Our eyes is one of the most sophisticated detector, by the way, in nature, because we can actually detect, optical signal. It has its own limitations, obviously, just like any detector, it has limitations, but it has quite amazing ability as well. It turns out that our eyes can detect some of the features of optical signal, not all of it, but some of the features. And here, symbolically, I'm showing this one, that our eyes can actually detect the intensity of the wave. And how do we actually perceive that intensity? We perceive it in terms of brightness. So we can all recognize, for example, if I look towards the light, I can see it's bright. But if I look, for example, away from the light and I look into the shadow, I would see it's dim. So it's a brightness is something that relates to the intensity of light. So what I show on the left is the physical quantities that I show. What I show on the right is the perception of that in the biology of visual system. So intensity is being viewed with our eyes as brightness. Now, how does the wavelength of the light being perceived by our eyes? That is being perceived as color. So if I send you a wave with a specific wavelength and our eyes can perceive that as yellow, okay, that's certain wavelength. But if I send another wavelength, it could be green, for example. So green light, yellow light, blue light, you name it, has each one of them has different wavelength. So our eyes can detect the brightness, meaning the intensity of light, and can also perceive color, which is related to the wavelength of light. But as I mentioned, optical signal has other properties. For example, polarization. Now, can our eye actually also sense the polarization of light? The answer is no. Actually, our eyes, human eyes, are polarization blind. So we cannot, sense the polarization of the eye. So what does that mean? That means if I send you a light that is yellow and that is bright, your eyes can detect that this is bright and your eyes can detect that this is yellow. But our eyes cannot detect whether the vibration of this signal is vertical or horizontal or circular or any other form of polarization. Our eyes are polarization blind. Now, as a footnote, I'd like to mention that there's a feature in human eye called Heidinger's brush that under very strong polarization, we can kind of sense that, but that is not used in imaging. So in other words, we cannot image, our eyes cannot image actually that polarization. So essentially, practically, our eyes is polarization blind. But here's an interesting feature that I learned from Ed Pugh when I met him, many years ago. And that is, there are animal species in nature that can see polarization of light. Now, this is quite fascinating. In other words, biologists and zoologists have discovered, going back to 1950s, discovered that some of the animal species in nature, their visual systems are sensitive to polarization of light. Now, which are those animal species? These are some examples I put on the screen. Honeybees, desert ant, flying water bug, octopus, cricket, cuttlefish, mantis shrimp, crustaceans, many classes of marine species. Their eyes can actually sense the polarization of light. So they can actually, quote unquote, see polarization of light. It's very hard for us as humans to actually feel that, what kind of additional information that will give us. But then as I go through my talk, we actually develop camera system that can actually show that to us. And we can see how the actually nature look like if our eyes were capable of actually detecting or seeing the polarization of light. By the way, historically, as an aside, I would like to mention that the first person, by the way, who discovered that honeybees has the eyes of honeybees has the capability of seeing polarization of light was this Austrian zoologist, Karl von Frisch. And he discovered very interesting, way that the honeybees can actually look at the polarization map of the sky, which I'm going to explain in a few minutes. And he later on won the Nobel Prize in 1973 in physiology and medicine because of he discovered the very interesting channels of communications among the species, which relates to this polarization as well. So it was a major discovery, by the way, that really shed light on how actually some of these species can communicate with each other. So why is the case, by the way? How is it that our eyes cannot see polarization of light? And how is it that some of the animal species in nature can? So let's go back to the basic of biology of human eye. Now, we have all seen this, in high school, in Hadaf High School, when we had, courses, طبیعی, of course, در مورد اون یاد می‌گرفتیم، در مورد بیولوژی چشم ما یاد می‌دادن. We all know, by the way, if you look at any textbook in biology, we are all familiar, of course, with the anatomy of human eye. And of course, this is the cornea. This is the lens of the eye. And it's interesting, by the way, that the back of the eye, this section is the sensitive part of the eye that actually is called retina. So what happens is when there's an object over here and light from the object comes to our eyes, this lens actually image that object on the back of the eye, and the image is formed on the back portion of the eye, which is called retina. And this retina consists of millions of photoreceptor cells. So there are millions of photoreceptor cells here in each of our eyes over here. And I'm going to show you an example of that in a second. And these photoreceptor cells, receive the optical signal, and they do something to that, which we're going to talk about. So this is, of course, very well known. And in fact, the eyes of many primates and many classes of vertebrates has similarities like that. I mean, you name it, many of the species that we know as vertebrates, their eyes similar to that. However, if you go to the insects, then the eyes are very different in insects. This is, for example, one example of the eye that could be from bees or from ants that you see over here. You notice this eye is very different, is known as a compound eye, and consists of many, many of these units that you see there. This unit is called ommatidium. So there are about, in let's say one single eye of honeybee or in fly or in ants, there are thousands of this ommatidium that you see over here. Now, it's interesting, by the way, that each one of these units, they have actually a lens on top of it. But that lens is not an imaging lens. Now, probably all of us have seen these Hollywood movies. I remember one of the, when we were a kid, there was this famous movie called The Fly. Probably some of us have seen that. Later on, they remake that later on in Hollywood, you know, I think in the 1990s. But back in 1950s, when we were kids, 1950s and 60s, there was this movie called Fly. And they were showing how the fly would see a scene. They were showing kind of like, you know, 100 little TVs. They would see that. No, that's wrong. That's not the way actually fly sees things, because unlike the human eye that we have only one lens, and this lens actually is an imaging lens. In other words, when you have an object, the image of that object would form on the back of a retina. In the insect, each of these points gets one data point. So it's a very, very poor resolution these insects have. So they don't have an imaging the way that we have it, you know, in our eyes. Nevertheless, that's actually is good enough for them, and that's why they can actually survive and go around. Now, what I'm going to show you in the next slide is that when you look at this retina, and there are millions of photoreceptor cells, let's pick one of them. I'm going to show you in the next slide and see how that looks like. So this is one example of a cell, photoreceptor cell in human called retinal rod. So it's a rod photoreceptors. And this rod photoreceptor, just to give you an idea about the dimension of that, this is about a few tens of microns. So something in the order of, let's say, like a 1/3 of the thickness of human hair is the length of it. But the diameter of that, of course, is much thinner. Obviously, compared to the human hair, and it's just about, you know, roughly about, you know, 7 to 10 microns. So it's about 1/10 of the human hair, and this of course would be about 30 micron. Now it turns out that this structure, this end of it is at the opening of the retina. So when the light is coming to our eyes, go through our lens and gets to the back of our eye, is this part that the light enters into this. And when the light enters into this, is being guided through this structure, and it gets to this section. Now this section is, if you enlarge that section, you're going to see something like this. This consists of many layers. They call it lamellar discs. And on this disc, there are many, many unit elements, photopigments. Now, these photopigments, you can think about it as receiving antennas. You can think about it as receiving antennas. So these little pigments basically capture the optical energy, optical signal. Now, it's quite fascinating, by the way. You notice that in this disc, these little receiving dipoles are randomly oriented. So جهت خاصی ندارن. It's just randomly oriented in that disc. So what does that mean? That means when the light enters into this and eventually gets to this region, doesn't matter what is the orientation of the vibration of the electric field in the signal. So our eyes cannot even detect that orientation. And why is that? Because these little receivers are randomly oriented. They don't have any preferred directions. So, and by the way, so what is the job of this photopigment? It's that they absorb optical energy. And when they absorb optical energy, chemically, they will be, they give rise to an interesting electrochemical process. And that gives rise to an electrical signal. And that electrical signal comes from here and goes to our brain. And that's how we can see. So every moment in our life, when we see something, is that that optical signal gets to our photoreceptors and being triggering that electrical signal. And this process is an electrochemical process. So that's how we can actually see around us. So this is clearly showing that this system cannot detect the polarization of light. It can detect the intensity and the wavelength. But if you look at some of those insects, their retinal, their receptor is very different than human. If you look at, let me show you, in this structure that you see over here, if you pick any one of these little units, that little unit consists of 7 or 9 parallel segments. And if you look at one of them, it looks like this. Now, this also would work as an optical waveguide. So light comes over here and being guided through this channel, just like what it happens in the human rod. But this one, when it goes, you notice that these so-called receiving antennas are not randomly oriented. For those insects, they're all oriented parallel to the specific directions. And that makes it very important, because when the light goes through this, if the vibration of the electric field is parallel with these unit elements, it absorbs more energy. But if it's perpendicular to that, it doesn't absorb that much. So that's why these species have the tools to actually detect polarization of light. Just like anything in nature, by the way, the system is not as simple as one would think, because in many of these species, this unit cell is not straight. It's actually twisted. So even though these cells have the ability to pick up polarization, but not all the cells in their eyes actually pick up polarization. Only a few of them have the ability to pick up polarization, and I'm going to show you why that is the case as we go. So when Ed Pugh and I started looking at this, and I became so fascinated by this field that I said, I want to learn about this, what's happening. First of all, how do these species actually detect polarization of light? But perhaps more importantly, why do they actually detect the polarization of light? So how of it is known, because just looking at this structure, but why? Why do these species actually use polarization sensitivity and human eyes cannot? Well, one main reason is navigations. As I mentioned, Carl von Frisch in 1959 discovered that honeybees can actually detect the polarization map from the sky, and based on that, they can navigate. Now, that's very interesting, by the way. So what is it about the polarization map of the sky? After all, what is a polarization map? So in this slide, I'm going to explain the physics of that. Imagine that there's an ant sitting over here, or any observer there. And this is, let's say, on some flat, desert, for example, and this is the sun. And what happens is that when the sunlight comes to us, because of the atmosphere that we have, sunlight starts to scatter. Now, this is also so common for us that we don't even think about it twice. In a regular sunny day, when we go out, we see that there is a bright, sky, okay? But the sun is only at one particular direction. And yet we always see the light coming from all directions of the sky. Now, why is that? It's because the light is scattered by the atmosphere. You've seen some of these movies that the astronauts, when they go to the moon and they're on top of the moon and they look at the sky, you notice that the sky is completely dark. It's black, except when the sun is, and except when the earth is, and when the other planets are. The rest, it looks black unless there are stars there. Now, why is that? Because the moon does not have atmosphere. So because moon does not have atmosphere, the light that's coming from the sun, it doesn't scatter, because moon does not have the mechanism to scatter the light. Whereas in Earth, we have the atmosphere. So when the light comes, scatters by this the particles in the molecules in the atmosphere, and that's why when we go out in a sunny day, we look like the light is coming from all directions. So, for example, in the morning when you go out and the sun is at one direction, if you look the opposite direction to the sky, you still see the light is coming from the sky, even though the sun is the other direction. So it turns out, by the way, that this can give rise to interesting pattern of polarization. I promise not to show any equation, but this is the only equation I'm going to show over here. And that is, if the ant is sitting over here and the sun is there, there's rays that coming from the sun, when it hits the many different elements of the atmosphere, is scattered. So depending on the angle of view that you have, you get a partial polarization coming according to this simple formula. So let's say, for example, if the alpha is 0, in other words, you're looking towards the sun, and you should never look at the sun because that's very dangerous for our retina. The light that's coming directly from the sun, polarization is unpolarized. So this degree of polarization is 0. And this sign is 0, so that becomes 0. But if you look at 90 degrees away from the sun, then this degree of polarization is rather noticeable. So you can easily, by the way, test this. If you have a Polaroid sunglasses, you can easily test this. In a regular day, if you go out and the sun is in one direction, let's say in the morning, the sun is rising. If you look 90 degrees away from the sun, that means you look up there and the sun is on the horizon. Then with the Polaroid glasses, if you actually rotate the Polaroid glasses 90 degrees, you see the intensity of light will change. And I remember I showed this to my daughter one day when she was little and we went to the beach at the noontime when the sun is right on top of us. Then if you look at the 90 degrees away from the top, you look at the horizon. And if you look at the horizon and you have a Polaroid sunglasses, you rotate it, you're going to clearly see that that actually changes significantly. So it's quite interesting, by the way, that the light that we see from the sky, depending on the direction that we are looking at, it has different polarization. So if I get this formula and I map it as a function of angle, then you get this. This is quite fascinating. In other words, this is a very well-known map called polarization map of the sky, originally studied by Rodiger Weiner. And so if you sit over here and this is the direction of the sun, depending what's the angle that you're looking at the sun, you get away from the sun, the degree of polarization is becoming stronger. So the thickness of this line that you see over here shows how strongly polarized the light is, and then become little and little become weakly polarized. So towards the sun, polarization is 0, 90 degrees away from that is like this. Now, it's quite interesting that when you and I go outside in the sunny day, we do not see this pattern because our eyes cannot detect polarization of light. So this feature is completely unknown to the human eye. And whereas those species, by the way, can actually detect this pattern in the sky. Now, this, of course, depends on your location and the direction of the sun. So during the day, as the Earth rotates, the relative location of the sun, of course, will change. And this map of the sky actually rotates during the day. Again, we don't notice that because our eyes are not equipped to actually notice this. But some of those species can notice this. So I'm going to show you what I showed in the next slide. So it's quite interesting, by the way, is that, for example, well, I'm going to show you how the insect can actually detect this. And from that, they can actually find where the solar meridian is. So it's quite a fascinating compass. Now, human beings, by the way, use compass because of the magnetic field of the Earth, North Pole and South Pole, and we use compass to find the direction in north and south. But these species use the polarization map of the sky that is invisible to us, but visible to them in order to find out where the solar meridian is during the day. And from that, they can navigate. And that's become particularly important, by the way, for example, for some of the species that they don't have any other milestone to navigate. For example, Northern African desert ants, when it comes out of its nest in the desert, their eyes, there are some cells on the top of their eyes that can actually look at the sky and see this polarization map. And then when they come out, they move their head in order to match this map with their receptors. And in electrical engineering, our friends in electrical engineering are familiar with this following terminology that we use. Is a match filtering. So essentially it matches, this map with the structure they have in their eyes. And from that, they know where the solar meridian is. And based on that, they can navigate and go to the food and come back. But in order to show this, we decided to actually go and take a camera and actually get a picture of the sky with the polarization filter in front of it and try to actually analyze that picture to see what we see. So let me show you this picture. This picture is taken using regular camera, regular camera that we have. In a sunny day, we went on the roof of our department, and we looked at the west. So it was 10:30 in the morning. So we look at the west, and 20 degrees away from zenith. So zenith is completely up on top of our head. And if we bring the camera 20 degrees away from that, this is the picture we see. Nothing interesting here. This is a picture that typically our eyes would see too. However, there is a polarization map over here that our eyes cannot see. But when we put the polarizer in front of the camera and we actually analyze the degree of polarization of the light that we come from there, and then we map that degree of polarization to some color coding, you see this. So this is quite fascinating. This is showing that this is the distribution of a polarization that our eyes do not see, but those species can. And this, of course, this color is not a real color. This color is just showing the degree of polarization on this scale over here. So it's just basically a color code that we have over here. So you notice here, the degree of polarization is very low, is about 5%. Whereas as you go away from the sun, remember the sun is somewhere here. So as you go away from the sun, the degree of linear polarization would increase up to about 50% polarization. The maximum would be 100%, of course. So it's a good amount of polarization that's come from the sky that is invisible to us. So we looked at the camera in different directions. In the west, that's the one I showed you. Look at the north, look at the east. When you look at the east, this is the sun that you see here. Of course, it's saturated picture, so we cannot show everything. These are essentially noise and the south. So you see that this is a very interesting map of the sky. And what happens to that species is that imagine now, let's say, for example, for the ant in desert. Now, ant is a two-dimensional species because they cannot fly. So it's only they walk on the surface. So for them, this map has to be projected, on the 2D surface. And when you project it, you get something like this. So this is interesting. This is the projection of that polarization image on the surface. And take a look at one of these species. This is a picture, by the way, of a cricket. And if you look at the compound eye that I showed you there, remember I showed you there are many, many of those units there. Now, each of those units looks like this and consists of about 7 cells that you see over here. Sometimes 9 of them. There are 2 of them here too. It consists of 7 cells. Now, inside of each of these cells, these lines that you see is the direction that the polarization can be picked up quite efficiently. So you notice that this little unit ommatidium has a preferred direction for detection of polarization. So let's look at this line as a preferred direction of that. And now let's come to the compound eye. This compound eye consists of many thousand of this ommatidium. And now this line that you see over here, each one of them is one of these lines. So biologists and zoologists actually studied this very carefully. And they find out that these units, they're not all parallel with each other. Each one of them, is tilted. Now the question is, why the evolution actually caused these ommatidia to actually form like this rather than being all parallel? And the answer to that is the polarization map of the sky. So actually their eyes adapted to the way the sky is. So these cells actually, they were adapting to this direction. And that's why they're not all parallel, because the projection of polarization map of the sky is not parallel. So one way that they can navigate, as I mentioned to you, they can come out and they can move their heads like this in order to match what the sky is with respect to that map. And from that, they know where the solar meridian is. Now, honeybees can actually also do that with flying. When they fly and look at the sky, from that, they can actually navigate and they get to their nest. And that's why Carl von Frisch in 1950s actually discovered that. And that led eventually to his winning the Nobel Prize in 1973. But this is not the only example in nature that polarization has been used. There are many examples. Let me show you another one. And this one is quite interesting, by the way. And this is something that accidentally, when we were studying this. Now I'm gonna right now, this is all background of the biology, but I'm gonna get into engineering and to see how we can use that in order to develop camera system that we did. So there's another interesting species called flying water bugs, Notonecta glaucoa. And this is studied by this biologist from Germany, Schumin, in 1984. And what he found out, by the way, that this insect has a very interesting, way of living. This insect actually lives under the surface of the water. So this is the surface of the water, and it's actually upside down under the surface of the water. And the eye of this species actually pointing downwards in the water. And the retina of the eye of this species have 3 segments. One segment is for the light that's coming from bottom of the water. The other one is the one that's coming from the total internal reflection. And the other one is coming from outside that we have there. And each of these segments of the retina, they are preferentially, advantageous to certain polarization. But this is not an interesting, this is very interesting, but this did not attract our attention. What really attracted our attention is how this species actually land on the surface of the water. And that's what they do, quite fascinatingly. So you may ask, okay, if this species is flying and would like to go on the surface of the water, how does the species know that that's water and not any other liquid? Well, the way they do it is quite interesting. As they fly, they actually tilt this body with a very special angle. And that is the angle that in physics of light, known as the Brewster angle. Now, Brewster angle is an angle at which, when you have a light reflection from a surface of an object, for that particular angle, the light that's reflected would be primarily only horizontal polarization. So the vertical polarization of light in that angle actually gets into the other region. It doesn't reflect that much. So this species actually, by tilting its body, it actually adjusts itself to that particular angle. And that angle, Brewster angle, varies from material to material. So for water, there's certain angle. For, let's say, other liquids, there are other angles. So this species actually can recognize that's a flat surface, but not only that, it's a flat surface of the water, nothing else. And then it just basically dives into the water and goes there and sticks to the bottom part of the surface that you see there. So when we were studying this one, we got actually quite fascinated by this feature of the biology, and we decided to see what we can do with it from application point of view in engineering, which I'm going to show you in a second. So up to now, by the way, what I was mentioning to you is something that biologists knew. And we were just learning about this from the work that biologists and zoologists have done. But we are physicists and electrical engineers, and we would like to see how we can use this. So over the series of the projects, Ed Pugh and I, and with our students and postdocs, decided to study various different applications of these features. Here I'm showing you about 6 of the application in the interest of time. I don't have time to go through all of them, but I'm going to show you some of them, some of the applications we have. So one of the things we discovered is that these species can see polarization, but how do they process this polarization? In other words, what is the neural system that they have, that they get this signal, and how do they process it? And without going into some of the detail of the physics behind that, what they do is that if you take a look at that single ommatidium that I showed you that consists of several cells, each one of them picks up different polarization. It turns out that the way they do it is that they get, vertical polarization and horizontal polarization. And the signal that's come from these 2 parts of the polarization, they have interesting neurons in their eyes that they look at the difference between these 2 intensities and try to see what that difference is. So I'm putting it in the generic terminology. In actuality, what the cells, it does is that it gives a signal, a temporal signal, whose frequency can change depending on the difference between these 2 intensities. So we were intrigued by this, that the nature has evolved such that this species can detect it this way. So we said, why don't we actually do that with a regular camera that we have? So what if I choose a camera, and I'm going to show you how we did it, and we put a polarizer in front of the camera and look at the image, and let's pick the image based on one polarization only, let's say vertical, and we record that. And then the same image, we're going to turn the Polaroid 90 degrees, polarization analyzer, and then record the image again. And then what we do, we go pixel by pixel, we subtract the two intensities to see what we see. So the idea was this one, that when we have an imaging system, like a camera, let's say we take two images from the system, we call it channel 1 and channel 2. The channel 1 would have one polarization, let's say vertical, and channel 2, we have another polarization, which is, let's say, horizontal. And then what do we do with this piece of information? We can add them together. In that case, you're adding the two intensities at every pixel, or you can subtract them. Now, this subtraction is the one we believe that the species actually use in their brain. Now, of course, we are not in their brain to see how they actually see the world, but we are engineers, so we can actually build a camera system that looks at the world and see what we see. And when we did that, it became very surprising to us, and I'm going to share some of those results with you. So we decided to test this. So in my lab, what we did, we created a tank of water, and we put a little bit of milk in this tank. Now, why did we add milk? Because milk is a very good scatterer. That's one of the reasons it's white, because it scatters, all the wavelengths of visible light. So we put a little of milk. Intentionally, we did that to make it murky, to make it very, low visibility in that regard. Then we actually built this aluminum disc. So with the machine shop, we built this aluminum disc, which you can see the size of it compared to a quarter. And this aluminum disc is a very thick aluminum disc, but one surface of that you see over here, we sandblasted it. We sandblasted it. Why did we do that? Because we wanted to make it rough surface. And because it's a rough surface, the polarization of that becomes very minimal when the light scatters. Except two patches over here is about 1 centimeter square, each one of them. We didn't sandblast it, but instead, using a sandpaper, we actually scratched it in a particular direction. You notice this is scratched in this direction, and this is scratched perpendicular to that. And we built another target with the same idea, but this time we put 4 patches. This is scratched like this is scratched like this, this is 45 degrees, and this is minus 45 degrees. And then we did that, with these 7 patches. Each one of them, rotated scratches, except the middle one still sandblasted. Now, why did we do that? And I'm going to show you the result, and you'll see why. The reason we did that is because when these are, scratched, when the light hits that one, the reflected light that's coming would have a polarization a little bit parallel with these, scratches. So we wanted to create different polarization pattern on this surface. So what we did, we said, okay, after we build this one, we put a target inside this, we put the light source there. You see the camera showing over here, and we put this camera in different direction. This is just one direction of that, but we actually bring the camera to the shadow face of this. So let me show you this. So the first image I'm going to show you is when we get the images with our camera and with the 2 channels of polarization, and then after we collect these images, then we go pixel by pixel, we post-process it, and pixel by pixel, we add the 2 intensities together. And when you do that, you get this. Nothing surprising over here. What you see over here is the shadow face of the target. So that target that I showed you, that I put in this tank of water, the light is coming in from behind the target, and the camera is looking into the shadow face of the target. And because we are looking at the shadow face of the target, you don't expect to see that much information. Very vaguely, you can see that there are, these 6 patches that you see over here. You notice that the patch in the middle is not visible at all. But these are vaguely visible over here, very little. Now, in the next image I'm going to show you next to this, we have the same target, same lighting, same camera. We didn't do anything else except the two images that we got, instead of adding pixel by pixel, we subtracted. And then we showed on that one. And when we did that, we got this. You see, the visibility significantly increased. And I would like to emphasize the fact that this is in the shadow face of the target. In other words, this imaging technique would allow us to actually see in the shadow. Even though the amount of light is very, very small, but we can see in the shadow. And not only we can see in the shadow, but we can actually distinguish the difference between these three patches and these three patches. Remember, these have different orientation of the scratches. And you notice this is much brighter and this is much darker, because when you subtract this, one of them becomes greater than the other one, and you see there. So this was very encouraging for us, that there is another interesting application that this camera can have, and that is underwater observation. In other words, with this technique, we can actually see objects better in the water, and by extension, you can actually see it better in the fog. So it can actually improve the visibility quite nicely. So, and we did a lot of this application. We built, whole, portfolio of different, structures and so on that this camera it can do. And so that was one category of applications that we did. Let me switch to another application area that we did. Now, this was the first application we did, as you see over here in Target. But then by then, we had our camera system developed, and our software was developed, how to actually process this thing, post-process, and so on and so forth. And now with that camera in hand, we could actually try different set of applications. One of the very different applications we had in mind is that, could we actually do an interesting surface imaging? I already showed you this slide about this species, and this actually inspired us. So I remember when I read this paper in the biology literature, I was very fascinated that this species can actually detect the surface of the water. So I was very excited. So I went to the lab, talked to some of the members of my group. I said, this is quite fascinating. By then, we already had the camera developed for other applications that I showed you. So I said, now that we have this camera, let's try to see whether we can see the surface of flat surface. In other words, if I have an object, we were not interested in water, but let's say we have a flat object like a glass. If I put something very, very minute on top of this flat surface, can I detect it much better? So we decided to do the following. Now I'm going to give you a quiz. If you look at this picture, what do you see over here? What do you think this picture is? Any suggestions?
Horizon.
First, it looks like that, Afshin John. Yeah, it looks like, the horizon near the beach you would look at. But no, it's not. What
I see kind of reflection on a glass, something like that.
I'm sorry, I didn't hear the first part of what you said. Tell me.
I see kind of reflection on a glass. There's a circle and line.
That's right. So let me tell you what this is. This is a cover of a CD, in the plastic cover of a CD that we have. And we put it on a book over here. You don't see the book over here. And the camera is taking a picture of this cover of the CD. At first, you might say, well, what's so interesting about the cover of CD? But we have put something on this cover of the CD that it's not visible in a regular imaging. And this is a regular imaging of a camera. This is just a simple camera. You put it there with the light coming and take a picture. You notice, by the way, you can see the circle of the CD. So the CD is here. You can see this. But there is something on the surface of this CD that is effectively invisible to our eyes. But what I'm going to show you now is with the same camera, same lighting, nothing's changing, exactly what you see over here. But what we do is that we take the image, the same image, with the two channels of polarization. We put two, one polarized vertical, the other one horizontal, two sets of images. And then what we're going to do, we're going to subtract those two intensities pixel by pixel. And then we process it. And when you do that, get this. Now you see actually what was on that cover of CD. It was a fingerprint. So this picture actually showed that we were able to actually detect a fingerprint. And we can detect a fingerprint with a simple camera by just equipped with the polarization difference imaging, the technique that we develop over here. You notice that this fingerprint is very visible over here. And clearly, if I show you the regular image, it's impossible to see that fingerprint. So this was, in a sense, accidentally, we noticed that because we were inspired by how that species, the flying water bug, can detect the surface of the water. We said, what would happen if we have a camera system that we can actually detect some minute variation of the surface? Now, why is it that this fingerprint is detected? It's because what is a fingerprint? Fingerprint is actually residual oil coming from the surface of our finger on a flat surface. And because the surface is no longer flat in that scale, when you send the light to that and the light reflects back, the intensity of the light doesn't change, but the polarization of that slightly changes. And our eyes cannot see polarization. That's what regular image, we can't see that fingerprint. But if we do the polarization camera, as we did, we can pick up that difference. And then we could see that. It was quite interesting, by the way. I didn't have any knowledge of how actually fingerprints are detected. After we did this, we started searching the literature and find out, how, for example, police departments, would detect the fingerprints. And there are, of course, two types of fingerprints. One is the fingerprints that you intentionally go and put your finger there and they can detect your fingerprints. That's just using with the laser scanning. But another set of fingerprints is the latent fingerprints, fingerprints that accidentally is left in the crime scene. Those fingerprints are much harder to detect. And the way that they detect that traditionally is going back to the technique at the beginning of 20th century. Essentially, they put a magnetic powder on that, and they put kind of like some tape, and they remove that. They call it lifting the fingerprints. And that's a very invasive way to detect the fingerprints, because if they don't do it right, the fingerprints is gone, and you cannot actually reverse that process. Our technique, by the way, introduced actually the new ways of detecting the fingerprint without even touching the surface. So it was completely non-invasive. You can do that. So anyway, so we decided to apply it to different things. So for example, this is a glossy cover of a book. This is a CD cover that I showed you, let's say a knife. And what would happen if you put the fingerprints on that? This is that glossy things you see. You can actually pick up the fingerprints, and then you can actually have quite an interesting directions there. In here, for example, this is a picture, a little metallic box over here, and intentionally put the fingerprints on that. And then by doing that, you can actually clearly see the fingerprints there. So this was one application. Let me give you the third category of application that we tried to do that. And this was actually, we got into this serendipitously, completely accidentally. Remember I showed you this picture just a few minutes ago when I told you that this is a picture that we wanted to detect the fingerprints. Now, when we put this CD cover and there was a fingerprint over here, we put it on a book, okay? But the book, just the book that we have borrowed from the library, okay? Not a big deal. But when we actually took this picture and I showed you this fingerprint, accidentally we noticed something interesting. We noticed that we were able to actually read what's in that on the surface of that book, University of Pennsylvania. So this was, we borrowed it from the library of the university. You notice that that was not visible in this case because this part of the book is in the shadow. And obviously we don't see things in the shadow. But now we are able to actually see in the shadow. So that actually triggered an interesting application for us. What would happen if we actually do the imaging in a shadow using polarization camera? Can we see that? Ordinarily, we cannot see it, but with this camera, we can see. So we decided to study this. So again, we went to the roof of our building. This is downtown Philadelphia that you see there. This is a building, skyscraper. And this is a regular picture that you see on the roof. You notice this is a sunny day. The clouds are, little clouds over here. You see these are, the shadow at the edge of the roof and some object here and so on. Now, Obviously, here we don't see what's going on in this shadow. There's some, structure there. But if we apply this technique, you can clearly see a lot of details that you see in the shadow. Look at the structure. You can actually see a very interesting structure that we have in this object there. Look at the clouds. Clouds turns out to be black because clouds would scatter light, and so the degree of polarization of that is very low. As a result, when you do the polarization imaging, this becomes actually black. Look at the glasses of the building. Those actually, the windows of the building would actually reflect light with the preferred polarization. You see, in this case, you can see the windows better than you can see it over here, and so on and so forth. So, and particularly this line is black, but then you can actually see in the polarization structure, you see it there. So then we try to actually apply this to natural scene. For example, this is just a flower bed in front of our department, and this is a regular image that you will see, in the grass and flower bed that you see there. And if you actually look at the polarization image of this system, you see this. You notice that, by the way, these flower petals become black, whereas the leaves are not. You see the leaves actually show up with a good degree of polarization, but the flowers turns out to black. One hypothesis we have, I mean, we are not biologists, but one hypothesis we have is that the insects that they actually get their food from the flowers, they're more attracted to this region because the polarization of light that's coming from here is very different than the one coming from, for example, from the leaves, rather than to the petal of this. But this is just a conjecture. We are not in their brains to see why they do that. So as a result, you can actually have very interesting segmentations of the imaging in the shadow. So this is a shadow in front of our building. There are actually two buildings here. One building is here, another building is there, and each one of them, they have their own overlapping shadows. But when we do this camera, you can actually see the shadow coming from different building has different polarization signature. So you can actually try to find, what these aspects has. Anyway, so I'm coming towards the end of my talk. So we started with that camera system with pointing the polarizer outside in order to do the proof of concept. But when we found out that it can have quite a fascinating application, we decided to make this camera more into microelectronic system. So rather than having the polarization, polarization filter being outside the camera, we decided to actually design a camera in which we put this polarization filter on the, camera chip that we have. So directly goes onto the camera chip. So that's the system that together, with one of my colleagues, Jan van der Spiegel, and we had this postdoc working with both of us, Victor Grue. And Victor Grue, later on, after he finished work in our group, he went and became a professor at the University of Illinois, Urbana-Champaign. And he actually developed this technique more expanded that. And now he's using it quite successfully for imaging, medical imaging. So this polarization camera, Victor did a fantastic job to expand it into application into medical imaging of that. So these are some of the microelectronic system that we have there. And that brings back to the end of my talk and the summary of that. First of all, I want to thank all of you again, my dear friends, Afshin and Mohandes Mohabet. Thank you so much for this kind invitation to me to give me a chance to come and talk with all of you. And I want to thank all of you for your interest in some of the work we do. I'm sorry that I gave this talk in English, but I'd be happy to answer any question you have in Farsi. If there are some aspects of that you need more explanation, I'd be happy to do that. Thank you all very much for your attention.
آقای دکتر انقطاع بسیار متشکرم. بسیار سخنرانی جالب بود. واقعا حقیقتا آدم بعضی وقتا نمیدونه چی بگه، با چه کلماتی یه پدیده رو توصیف کنه. من فکر میکنم که اگر اجازه بدید یکی چند دقیقه شما یه استراحتی بکنید، اگر احتیاج دارید شما یه نفسی تازه بکنید 2-3 دقیقه، بعد دوستان آرام آرام سوالشون بکنن. دوستان من آقای فروزی و آقای صبا لطفاً سوالا رو هدایت بکنید و عزیزانم اگر لطف بکنن از فیچر رایت هند استفاده بکنن برای چیزشون. پس اجازه بدین یک 2-3 دقیقه آقای دکتر انقطاع استراحتی بکنن و بعد آرام آرام ما وارد مرحله پرسش و پاسخ بشیم. دوستان رو به ترتیب نوبت چیز کنید، صدا کنید.
یک سوالی توی چت هست که از ابتدای بحث تقریبا هست اونجا، اگه اجازه بدید من اون رو میپرسم. پرسیدن که Hi Nader John, how do we know these fish see the polarization of the light?
خیلی ممنون. سوال خیلی عالی هست و خوشحالم که آقای همایون، من نمیدونم آقای
همایون رشید پور.
آقای رشید پور، دوستان همایون جان الان اینجا هستی، خیلی خوشحال شدم که این سوال کردی. حتما خوشحال میشم که جواب بدم. این نکته خیلی جالبی هست. من موقعی که با اون استادی گفتم از دانشگاه دپارتمان سایکولوژی، پروفسور اد پیو. By the way, I forgot to mention that he was a professor of Department of Psychology, but when I got to know him, I found out that he's a neuroscientist. Even though he is in Department of Psychology, but the psychology department at Penn is not like, therapist that's sitting there and giving me your problems. It's just the actually neuroscientist. Anyway, so this was actually a question I asked him at that time. I said, Ed, how do you know that this species actually can see polarization of light? And he took me to his lab and he showed me very interesting experimental setup that he had, how to actually detect species can see polarization of light. Now, we as a human being, if they shine a light to us, and whether we see it or not, we can say it. So we have the ability to talk and say that. But how does the fish or other species can actually do that? So he introduced me to a very interesting scientific technique that he was one of the pioneers of that. It's related to the Pavlovian experiment. I don't know, I'm sure many of you are familiar with this Pavlov experiment that Pavlov, the famous biologist, what he did once is that there was a dog, and whenever he actually give a food to dog, he actually rang a bell. So every time he was giving a food to the dog, he was ringing a bell. And after several repeats of this, then he would just ring a bell without giving any food to the dog, and the dog start to salivate. In other words, dog actually connected the sound of the bell with the food. And so every time the food was given to the dog, it was ring a bell. So over time, that association will cause that he would feel hungry and he would salivate. This technique, Ed told me, that is known in physiology. So the way they're doing for the fish in his lab is that he was putting a fish in the tank of water, but in a little bit confined region. So the fish cannot swim away. So there was a little bit in the confined region. And then the optical system was in front of this fish. So it would send the light to this fish. And then the tail of the fish, there was 2 electrodes in the water close to the tail of the fish. And these electrodes was connected to some, very low voltage signal. So whenever he was sending the light with the polarization to this fish, he would actually trigger that voltage a little bit. And that trigger of the voltage sent a little bit of current in the water and basically shock the fish. So every time he was actually sending, this one there, the fish was shocked by that. So he repeated that many, many times because, of course, dog is much smarter than the fish. So it takes much longer time for the fish to associate that trigger with the light. So after many of this trial, then, by the way, also he was also monitoring the heartbeat of the fish. So whenever the fish would get that shock, it would actually, his heartbeat would go up. In other words, it would scare. So, and associate that with the polarization of light. So after many tries, then he stopped actually giving the current, and then shining the light to the fish, and then measuring the heartbeat of the fish. And based on that, he was associating that the fish can see polarization of light. So it's a very interesting technique. It took a long time, you know, for him to do that. But it's just based on these physiological aspects that would do that. But that's an excellent question. How the like we did. Also, I mean, the biologists and zoologists that they did that for the insect. For the insect, it's harder because controlling the insect is very hard. So Rodiger Weiner, for example, was basically putting in the desert, you know, this Polaroid on top of let's say the ant, and basically disturbing the polarization pattern of the sky. So the ant would actually be going to a different direction that originally wanted to go, because it completely disturbed the polarization pattern for the ant, and that's how he measured this.
خیلی ممنون، دستتون درد نکنه. آقای مهندس سعد دستتون بالاست، بفرمایید قربان.
سپاسگزارم. سپاس فراوان جناب دکتر انقطاع، بسیار پرزنتیشن عالی بود. من سوالی که دارم در واقع سوالی است که احتمالاً آزمایش نشده، نمیدونم، ولی میخوام ببینم که نظر شما چی هست. اگر این دوربینی که شما درست کرده بودید، اگر فرض کنیم که به حالت عینک در بیاد با تمام اون قدرت پردازشش، و اگر انسان بخواد این عینک رو استفاده کنه و به صورت پولاریزه نگاه بکنه، مغز ما چه حالتی اون رو پروسس خواهد کرد یا ما چه خواهیم دید؟
Very excellent question. Another excellent question. قبل از اینکه من جواب این سوال شما رو بدم، بذارید یه سوال دیگه مطرح کنم، بعد برمیگردم به این مسئله. و این سوالی که به نظر ما اومد در اون موقع که ما این اولین، یعنی ماهای سالهای اولی بود که این کامera رو درست می‌کردیم، اینی که خیلی خب ما میتونیم این اینفورمیشن رو از طبیعت بگیریم و ببینیم این polarization information در طبیعت چجوری هست. ولی سوال بعد اینه که خیلی خب ما این اینفورمیشن رو گرفتیم، چجوری این اینفورمیشن رو نشون بدیم؟ Because at the end a human observer is looking at something. So somehow this polarization information has to be mapped into something that the human eyes can see. So what kind of gadgets do we have around us that we can see the image of something? Well, that gadget is right now in front of you, your monitor, your computer monitor or TV monitor. So the TV monitor is actually maps what the camera is taken, and then it brings it to us. Now, if you look at the TV monitor, by the way, right now, we all have, a color monitor. Many years ago, when we were very young, we used to have just a black and white monitor, but now we all have color monitor. So color monitor, of course, would give us what? It gives us the color perception and gives us the intensity. So that's what we can see, actually what the real intensity and real color is. But we were thinking at that time, is it possible to actually invent a monitor that actually shows polarization? It would be nice, if we have a monitor that in addition to intensity and color, which the current monitor would do, also shows polarization. But the problem is that even if we could invent such a thing, the human beings would not be able to see it. In fact, that's one of the reasons that polarization monitor was never invented. Because if you invent the polarization monitor, no human being can actually see what that additional information is. And you don't want to invent a monitor for insects, for example, because we'll use it. So as a result, what we decided to do is rather than do that, try to get the polarization information and map it into something else that the human eyes can see. Okay, so what can we see? Well, obviously intensity that I mentioned, brightness is one of them. Wavelength, which perceive as color, is another one. But what else can we see? I mean, our eyes can see this. But actually, it turns out that our eyes have other interesting abilities. For example, imagine the following. Unfortunately, I don't have that slide with me, but we did this experiment. Imagine the following. Imagine that you have on your computer screen, let's say you have an image, and this image consists of many little dots. And let me assume that these little dots are all moving around randomly. Remember when we were kids, when we were looking at TV, in Iran, when there was no TV program, we had this thing, we used to call it barfak. television چیز نشون میده. So that's random things moving around. Okay, so our eyes can see that random things. However, if you look at those random dots and make some of those dots move together rather than randomly moving around, but some of them move together, our eyes have the ability to immediately notice that. Our eyes has a very interesting ability, by the way, in moving the objects together, and particularly our peripheral vision. Our peripheral vision is actually much more sensitive to motion than our central part of our vision. The central part of our vision is called macula. So macula is the region of the eye that is right in the central axis and has a very high resolution. So when you and I are talking to each other, we are looking at each other because we would like to see the highest resolution of the image of you, and you're looking at me. But as I'm looking at you, on my peripheral vision, the resolution is not that high. So in fact, you can always test it, and it's very easy to test. If you're looking at the monitor, move your hand on the side of your face, but don't look at your hand. And you notice you don't see the high resolution on your hand, other than unless you bring it right in front of you. When you bring it right in front of you, you can see it in all the detail. But when you bring it to the side, you don't see all the detail. But the peripheral vision has a very interesting ability that the central part of the vision does not. And that is the peripheral vision is very sensitive to motion. And you can actually test that. If you're looking at the monitor right now, the frame of the monitor goes 30 some per second. But we don't see that motion because the central part of our vision does not have that temporal resolution. But the same monitor that you have, if you look to the side and with the peripheral vision, look at your monitor, you may see flickering that happens there. And that's just because the peripheral vision is much more sensitive to motion than the central vision. Now, as a side issue, you might say, why is that? Why our eyes have much more sensitive to motion on the side, but not in the central part of our region? There are several reasons. One thing is the central part of the eye has the highest amount of data. It's very, very tiny photoreceptor, so it's a very high resolution. You can see all the details. But the side does not have that much resolution, but has a good resolution for speed. So we can actually pick up that quite nicely. And the reason is because during the evolution, our eyes evolved in such a way to actually be very alert of anybody who attack us. And usually when there's a prey attacking us, attack from the side, not from the front. Because if the front, we can easily see it. But in nature, you know, if somebody in one species attack another species, it usually happen from the side. And that's why the peripheral vision of many animal species, particularly primates, evolved in such a way to be sensitive to the motion on the side vision rather than the front. So coming back to this, the question is that how do we actually able to see this one? Yes, you need to map the polarization information into another quantity that our eyes can see. If you notice, by the way, let me share my screen to show you the last slide I was showing. Where is it? I think it's this one. This picture that I showed you, remember at the early part of my talk, you notice that I showed the degree of polarization, very small, 5% over here, and this is about 50%. So the way I could show that is I had to map it into a color, because otherwise our eyes can't see that polarization. So we have the information there, but we have to map it to a quantity that our eyes can see. Now, this color is not the real color of the sky, obviously, but it's representation of the degree of polarization. So bottom line is that, yes, our eyes have limitations, obviously, just like any things have limitations. And we get the information from the nature, but somehow we have to translate that into a quantity that our eyes can see. And sometimes the color would help, sometimes the motion of the particles would help, and sometimes texture would help, but the information is there.
مرسی. آقای مهندس حسین خواه بفرمایید، دستتون بالاست. صداتون بسته است البته قربان.
سلام عرض کردم و تشکر فراوان. طبق معمول لذت بردم و بسیار اینفورماتیو. جناب پروفسور، من سوالم اینه که اشعه شرنکوف که حتما توی فیزیک هسته‌ای حتما دیدیدش یا تو راکتورهای اتمی، آیا اون هم بر اثر پدیده پولاریزیشن ایجاد میشه یا خیر، یا یه فنومن دیگه ایه؟
خیلی ممنون از سوالتون. سوال جالبیه آقای حسین. شرینکوف رادییشن فنومن کاملا جدایی هست از پولاریزیشن، به خاطر اون نیست. من میتونم خیلی کوتاه توضیح بدم که شرینکوف رادییشن چجوری ایجاد میشه. همونطور که گفتین شرینکوف رادییشن موقعی ایجاد میشه که یک پارتیکلی که چارج داشته باشه، مثل الکترون، وقتی الکترون حرکت میکنه در یه محیطی، این الکترون با خودش الکتریک فیلد همراه میبره، بلکه الکترون الکتریک فیلد داره و این الکتریک فیلد با خود این الکترون میره. نه، electron cannot go faster than velocity of light. Nothing can go faster than velocity of light. So obviously electron moves slower. And as it moves, this field around the electron moves with it. Okay, now, but if the electron is in the medium, in which the velocity of light is lower in the medium, and if the electron would go faster than velocity of light in that medium, but not velocity of light in vacuum. Nothing can go faster than velocity of light in vacuum. But because velocity of light in the medium is lower, it is possible that the electron can go faster than that velocity. When that happens, what happens is that the field that's generated by the electron falls behind. It becomes like a shock wave. You know, shock wave is exactly happens like this. If the airplane goes with a speed faster than velocity of sound, we know that دیوار صوتی رو
میشکنه.
دقیقاً دلیلش اینه که وقتی اون هواپیما حرکت میکنه، اون مکانیکال موشنی که ایجاد میکنه، یعنی آکوستیک ویوی که ایجاد میکنه،
بله،
آهسته تر میره تا خود هواپیما. در نتیجه خود هواپیما از اون صدای جلوتر میره، تمام اینا اینجا جمع میشه پشتش و یه شاک ویو ایجاد میکنه. و به همین جهت اون شاک ویو خیلی قوی هست، برای تمام اون چیزا با هم جمع میشه. Cherenkov radiation is the electromagnetic version of that. And when the electron goes in a medium, it has to be in a medium, because in the vacuum it cannot do that. In a medium, when the electron goes faster than speed of light in the medium, but slower than speed of light in the vacuum, then it creates this Cherenkov radiation. And yes, but that has a special polarization of its own, but it's not generated because of polarization.
بسیار عالیه دکتر. من بایستی این سوال جواب رو برای آرش انقطاع تعریف کنم.
حتما سلام برسونید.
حتما بزرگی شما رو میرسونم. خیلی متشکرم.
خیلی ممنون، مرسی. آقای مهندس امینی بفرمایید، صداتون بسته است.
سلام مجدد عرض میکنم و خیلی تشکر آقای دکتر انقطاع، واقعا لذت بخش بود پرزنتیشنتون. سوالی که من داشتم، آیا کاربردهایی از این روش در تلسکوپ های فضایی یا دوربین های برد زیاد میبینید که مثلا بتونه بر اساس این پولاریزیشن تصاویر خیلی دقیق تر و کامل تری ایجاد بکنه؟
بله، خیلی ممنون از سوالتون. بله، به طور کلی این سوالش خیلی جالبی شما کردین. بگذارید من جوابش رو خیلی کلی تر بدم، نه فقط در مورد مثلا فرض کنین تصویر برداری از کهکشان ها اینا، ولی به طور کلی وقتی شما یک تصویر برداری بخواید بکنین در محیطی که لایت باعث بشه که سکاترینگ باشه، مثلا فرض کنین توی آب وقتی نور وارد آب میشه خیلی سکاترینگ زیاد داره، یا مثلا فرض کنین توی مه، توی فاگ سکاترینگ زیاد هست. همینطور توی اتمسفر سکاترینگ زیاد هست. به همین جهت میگن که لایت پولوشن، به همین جهت هست که معمولا پلانتاریوم‌ها و اون رصدخانه هایی که نزدیک شهرهای بزرگ هست کارشون خیلی سخته، به خاطر اینکه نوری که از شهر میاد وقتی به اتمسفر میخوره باعث پراکندگی نور میشه، در نتیجه نوری که از ستاره ها میاد خیلی ضعیف‌تر خواهد بود. به طور کلی وقتی شما میخواین تصویر برداری بکنید در محیطی که سکاترینگ لایت زیاد هست، این مسئله پولاریزیشن کمک میکنه. چجوری کمک میکنه؟ به این ترتیب که وقتی که لایت پخش میشه توسط این مثلا اتمسفر یا توسط مثلا خود آب، اون یه پولاریزیشن خودشو داره، ولی آبجکتی که شما دنبالش هستین یه پولاریزیشن دیگه داره. در نتیجه اگه این کامera رو طور درست بکنیم که این پولاریزیشن دیفرنس ایمیجینگ بک‌گراند رو کم بکنه و پولاریزیشن دیفرنس ایمیجینگ خود آبجکت رو زیاد بکنه، در نتیجه ویزیبیلیتی زیاد میشه. و در تایید حرف شما میتونه اپلیکیشن هایی داشته باشه توی تصویر برداری از در فضا، از جاهایی که ممکنه اسکاترینگ زیاد باشه، به خصوص به خاطر اتمسفر زمین. و همین مسئله که ما اینجا نشون دادیم، ببینید الان من اینو دوباره این یک دقیقه من اینو نشون بدم به شما، یادآوری بکنم. این تصویری که من به شما نشون دادم در واقع بر همین مبنا کار میکنه، به خاطر که شما ببینید این بک‌گراند که شما در اینجا میبینید این همون نوری بود که از پروژکتور میومد به این آبی میخورد که توش مقدار شیر ما اضافه کرده بودیم که اسکاترینگ باشه، در نتیجه خیلی نور زیادی به کامera میرسید. و ما این قسمت تارگتی که توی شادو ریجن بود نمیتونستیم ببینیم، ولی همین الان با این پولاریزیشن دیفرنسینگ که انجام دادیم این قسمت تقریبا میشه صفر، ولی این قسمت هایی که صفر نیست نشون داده میشه. یعنی شما میتونین بهش میگن کلاتر ریمووال، یعنی اون قسمت هایی که مورد علاقه شما نیست در تصویر برداری اونا برداشته میشه و اون تارگتی که میخواین ببینین در واقع سیگنالش قوی تر میشه. به این صورت میتونید شما ببینید. در نتیجه میتونه اپلیکیشن داشته باشید در هر صورتی که لایت اسکاترینگ وجود داشته باشه. بله.
خیلی ممنون دکتر. آقای مهندس نصرتی دستتون بالاست، بفرمایید. صداتون هم بسته است قربان. صداتون بسته است قربان.
میکروفونتون بسته است آقای نصرتی.
باز شد قربان؟
بله.
سلام عرض ادب قربان خدمت شما و همه دوستان. خیلی ممنون بابت آنچه که امروز به ما یاد دادین و اضافه کردین به دانش‌های خود اندک بنده. من یه سوال خیلی ابتدایی دارم قربان و اونم در مورد این هست که ظاهراً بعضی از حیوانات تصویرهای سیاه و سفید فقط می‌بینن و رنگی دنیا رو نمی‌بینن. سوال من این هست که اون قضیه به این داستان پولاریزیشن هم ربط داره و اصلا کلاً کاربرد این قضیه در موضوعات سیاه و سفید و دیدن تصویرهایی که رنگ درش مطرح نیست چجوری احتمالاً تفسیر میشه یا کاربردی داره یا توضیحی توش هست نه؟
لطف دارین آقای نصرتی، خیلی ممنون از سوالتون. سوال جالبی بود. قبل از اینکه من جواب این سوال مستقیم بدم، بذارین یه چند دقیقه خیلی کوتاه صحبت بکنم در این صورت که چجوری اصلا چشم ما میتونه رنگ رو تشخیص بده. این مسئله جالبی هست. اگه با اجازهتون من دوباره اینو بذارین اینو من ببرم، یه اجازه بدین که من ببرم این قسمتی که گفتم، همون اول صحبتم که صحبت کردم.
بله.
با اجازه شما من اگه یادتون باشه آقای نصرتی، این سلاید من به شما نشون دادم، گفتم این همون پیکچر بود که دوست من پروفسور الپیو به من نشون داد. حالا این البته در مورد این چشم اون ماهی خاص هست، ولی اون مسئله رو بذاریم کنار. شما متوجه میشین که این قسمت‌هایی که به صورت circular cross section هست، این قسمت‌ها بهش میگن cone photoreceptors. cone. Now this double cone is specifically for that species. ولی چشمای ما هم این cone photoreceptor رو دارن. اگه دقت کرده باشین این قسمتی که در مورد human eye صحبت می‌کردم، این human eye رو، این قسمت رتینایی که می‌بینین خیلی چندین صد میلیون فوتوریسپتور توش هست.
بله.
قسمت زیادی از این فوتوریسپتورها در واقع این راد فوتوریسپتور هستن. اوکی. ولی فوتوریسپتورهای دیگه‌ای هم تو اون رتینا هست در رتینای ماها که بهش میگن cone photoreceptors. Okay. Now, so what's the difference between cone photoreceptors and rod photoreceptors? Now, actually, it's quite fascinating. Rod photoreceptor is the one that you see over here. Cone photoreceptors is the shape of it is just like a cone. Again, it does the same job. You get the light and you take it there. However, cone photoreceptors is sensitive to certain range of wavelengths. So human eye have one class of rod photoreceptors that you see over here, and 3 classes of cone photoreceptors. 3 different classes. Now, in each one of them, there are millions of them in each eye that we have. Now, what are those 3 classes of cone photoreceptors? One class of that is sensitive around the red color. Another one is sensitive around the green color. Another one is sensitive around the blue color. So when I say sensitive, I don't mean just only one wavelength. In fact, they receive a lot of wavelengths. So it's kind of like a pattern like this. So it's sensitive. The tip of it is the wavelength at which you have green, and the wavelength you have blue, and the wavelength that you have red. خب چشم ما این 3 تا فیلتر رو داره که فوتوریسپتور به اضافه این راد. نه وقتی که نور وارد چشم ما میشه، وقتی مثلا من یه ویولنگت چشم شما میفرستم که مثلا ویولنگت زرد رنگ هست. خب این 3 تا که من گفتم هیچ کدومشون به نظر زرد نمیاد. یکیشون گرینه، یکیشون بلو هست، یکیشون رد. ولی به خاطر اینکه این دیستریبیوشن دتکترش در واقع چیز هست، وایت هست، وقتی شما یه طول موج رو میفرستی، هر 3 تای اینا یه قسمتش رو جذب میکنه. اونی که رد هست یه قسمت رو جذب میکنه، اونی که گرین هست یه قسمت همین یلو رو جذب میکنه، اون قسمتی که بلو هست جذب میکنه. منتها این 3 تا آتپوتی که از این 3 تا کون میاد میرن در مغز ما و بستگی داره که در واقع مگنیتود هر کدوم اینا چی باشه، مغز ما تعبیر میکنه که اون طول موج زرد هست. مثلا شما الان واسه که تنتون هست رنگ زرد هست. این رنگ زرد البته نه تو مانیتوری که من دارم میبینم، ولی اگه من تو همون اتاقی بودم که شما نشسته بودین، نوری که از لباس شما به چشم من میرسه یه ویولنگت خاصی داره. این ویولنگت خاص وقتی وارد چشم من میشه و اون فوتوریسپتورها رو بهش میرسه، اون 3 تا کاتگوری فوتوریسپتورها این یه طول موج میگیرن، آتپوت های اینا فرق میکنن، ولی مغز من تشکیل میده که بر مبنای این کامبینیشن آتپوت this should be a yellow light and that's what we detect, the yellow light. Now different species would have different cone photoreceptors. In other words, it's not necessarily the same as red, green, blue. It could be a different one. Some of them could be only one photoreceptor. In that case, they would not detect color because they have only one output of the photoreceptor coming out. It's not clear whether this depends on the change of the wavelength or change of the intensity. So they don't have enough information. That's why they don't see color. Now, it's interesting, by the way, that you might say, okay, this is very interesting, but why the nature is evolved that we have 3 cone photoreceptor and 1 rod photoreceptor. By the way, when I say 3 and rod, 3 and 1, I mean there are millions of each one of them. So that's it. It's very interesting. Rod photoreceptor, the one that you see on the screen, is very sensitive to light. Very sensitive. In other words, very small amount of light can excite this rod. But the cone photoreceptor sensitivity is low. So what does that mean? That means if I go to a dark room or a room with a very low light, the cone photoreceptor in my eyes are not activated, but the rod photoreceptors activated. And because I only have one class of rod photoreceptors, I cannot detect color. Have you ever tried that? If in the, dark night, you go out in the dark night, you don't recognize color. It's all bluish. But as soon as you turn on the light, then you can see the color. Why? Because when you turn on the light intensity would go up, the rod photoreceptor will be saturated, but the cone photoreceptors will become activated. And because we have 3 of them, we can actually find what the color is. And that's why the monitors were invented based on the 3 color RGB. You have heard about it, red, green, and blue. So while what you're looking at me right now, and you look at the color that's coming from my sweater, the light that's coming from your monitor, the wavelength of that light is not necessarily the wavelength of the light that's coming from my sweater. But the monitor creates those 3 RGB in such a combination that your eyes think that the light is that wavelength. So essentially, the monitors are fooling our eyes to pretend that we are seeing yellow light. But what that's really coming from the monitor is red, green, and blue, but with the different weights between them. So that's why some species, they do not have 3 class of cone photoreceptor. They may have 2. They may have 1. In fact, the species in the very deep ocean, I mean, they don't see color. They just have very, very sensitive photoreceptors that they get few photons. And they don't need it. I mean, we need it because we are in an environment that we have a lot of light because of sun. And that's how human eyes evolved. And also the other species, like, cat, dogs, and so on, they have also evolved, they have certain different aspects of the cone photoreceptors as well.
مرسی دکتر. من چون خودم به سوالی نسبت به این صفحه دارم، اگر ممکنه حالا سفر رو بردید از سینا جان اجازه میگیرم قبل از ایشون من سوالام میپرسم. این راد فوتوریسپتورایی که گفتید اون دیسکا به طور رندوم قرار میگیرن، آیا این به این معناست که مثلا در جمعیت 8 میلیاردی این امکان وجود داره به طور رندوم یه نفر نور پولارایزد رو ببینه، یا این رندوم بودن چنین آپشنی رو برای هیچ کسی ایجاد نمیکنه؟
تا اونجا که من میدونم ایجاد نکرده برای کسی. یعنی برای که نگاه کنید، شما هر کدوم این دیسکاری که نگاه کنید there are millions of these pigments there. It would be very unlikely that these pigments would be oriented in one direction. In the insect, because they're anchored on the wall of their photoreceptors. In the human eye, that is in this lamellar disc, is randomly oriented. However, that's actually a very interesting question, Aysabo, if you ask. If you go over here and we look at the human eye and you see this is the optic nerve. Now, this is interesting because all these photoreceptor cells that we have over here, their nerve that's coming out of that, eventually they all bundles away and go through this optic nerve. When they bundle away going through the optic nerve, if the light is coming from here, it's highly polarized, parallel with those bundles, it may have a very small effect on that. So that's called Heidinger's brush. That's a phenomenon called Heidinger's brush that some people with a very strong polarized light, they may be able to notice that. But it's not used for anything. I mean, it's not for imaging. It's not like that at this point you see vertical polarization, at this point you see horizontal polarization. That's impossible. That we don't see. Only here is a very, very, I tried with my own eyes and I cannot see polarization. So that was very clear.
Okay, thank you very much. مرسی. سینا جان شما دستت بالاست، بفرمایید.
مرسی بهشت جان. سپاس فراوان دکتر انقطاعی عزیز. من نخست میخواستم معذرت بخوام از سوال ابتدایی که دارم، البته راجع به نور و همچنین ربطش به کوانتوم، یعنی ورد کوانتوم که واقعا نور یک elementary به هر حال پارتیکل هست. اگه اجازه بفرمایید توضیحات شما بسیار یه ایمیج خیلی جالبی به من میده، از این نظر که اون نیچرهای لایت رو که به صورت پارتیکل یا ویو هستش ترادیشنالی، الان راجع به پولارایزیشن وقتی صحبت میکنین ناخودآگاه من اینو وصل میکنم به اون فیلد نیچر آف لایت و اینکه آیا من این تصورم اشتباه است که فکر کنم این حالت فیلدی که لایت اگر قبول دارید که این حالت رو نشون میده تو پولارایزیشن، میتونه در اینتراکشن باشه با المنت های دیگه کوانتوم که در فضا پخشن و این پولارایزیشن میتونه یه ایندیکیشنی از این باشه؟
سوال خوبی کردید، به خاطر اینکه میتونم اینجوری توضیح بدم. تو دیسکاشنی که من امروز داشتم با شما، من اپتیکال سیگنال رو به صورت ویو توضیح کردم. And because it's a wave and because of the electric field is oscillating with certain frequency and of course there's a wavelength there, this orientation of the vibration of electric field by definition is a polarization. So whether it oscillates in this direction or in this direction or circularly polarized and so on, that's what we have. However, you brought up a fascinating question too, and that is, can we actually describe this as a photons, in other words, the particles of light? And yes, you can do that. You can relate to that. In fact, it's very interesting. The rod photoreceptors that I was mentioning in answer to our Nosrati, the rod photoreceptor is so sensitive that only a few photons can actually activate them. That's why, it's amazing, by the way, that the human retinal rod that we have is very sensitive to light, and only a very few photons can excite them. Now, you can, and now that's in biology. Now let's come into the physics of the problem. In the physics of the problem, you can actually have a photon that represents polarization. Yes, I mean, in that case, sometimes we use a different terminology. We call it, for example, spin of that. Then when we go to the quantum aspect, then if you look at, elementary particles, in physics, then elementary particles would have different quantum IDs, so to speak. So one of them is spin. And then translate that into the language of photon of electrodynamics, then of course becomes spin. Part of that relates to, they call it, orbital angular momentum, but mostly it relates to the basically spin of the photon. Again, human eyes cannot detect that, cannot detect the spin. But yes, I mean, in short, in summary, I think interaction of the light with biology can also be described in a quantum physical way. Yes, it can be described in a quantum physical way. Now, if your question relates to interaction of light as a photons with, let's say, other atomic structures, yes, of course, that has to be quantum. I mean, that's the interaction of photons with atoms. And that really goes back to the fundamentals of interaction of light with matter in the universe. Because at the bottom line, we have a light and we have interacting with the atom. And in that level, then we need to actually use quantum physics. That goes there. Biology, because biology has a much more complex system because of the redundancy of the system. The cells, even though we sell the unit cell, but the unit cell, of course, itself is very large. I mean, compared to molecular structures that we have. So that's actually led to the molecular biology. So that's a very active field and cellular biology.
Yes.
خیلی ممنون آقای دکتر. آقای مهندس حمیدی سوال دارید؟ بفرمایید. بعد از ایشون یه سوال تو چت هست و بعد برمیگردیم به حضار. بفرمایید آقای حمیدی.
خیلی ممنونم آقای دکتر انخدا. خیلی مطالب جالبی گفتید و خیلی لذت بردم و یاد گرفتم. بی‌نهایت ممنونم. راستش شما مثالایی زدید در مورد حشرات و یا در مورد ماهی برای اون پولارایزیشن آف لایت که برای جذب این نورا. در مورد گیاهان حالا نمیدونم، میخواستم ببینم تا چه حد، ببخشید من این تصویرمو قطع کنم که اشکالی نباشه، که در مورد گیاهان که به طور کلی همچنان که خودتون اطلاع دارید که 3 گروه کلی گیاهی هست که نورپسندن و سایه پسند و بینابین، و یه سری هم مثلا خب در زیر آب زندگی میکنن. برای جذب این نورا خب حیات و بقای اینا بستگی به نور داره و از این نظر گفتم ببینم آیا تحقیقاتی در اون زمینه پولارایزیشن آف لایت رو برای سیستمای خاصی که یا گیاهان در رابطه با میزان نوری که میگیرند این یک سیستم خاصی هستش و تحقیقاتی در اون زمینه هم انجام شده یا نه؟ خیلی ممنونم.
خیلی ممنون از سوالتون آقای حمیدی. واقعا نمیدونم، جواب این سوال رو نمیدونم که توی پلانت بیولوژی آیا در این مورد تحقیقاتی شده نه. سوال خیلی خوبی هست. منم کنجکاو کردین الان که ببینم که آیا واقعا تو بیولوژی اینطور هست یا نه. ولی یه چیز رو همونجوری که تو پرزنتیشنم گفتم، تو در واقع قسمت آخر پرزنتیشنم بود که ما وقتی کامرای خودمون استفاده کردیم و به گل‌ها و در واقع برگ‌ها و اینا نگاه کردیم، دیدیم که تصویر این گل‌ها و برگ‌ها با این پولاریزیشن میتونه تصویر متفاوتی داشته باشه. همونطور که نشون دادم برگ‌ها مثلا بیشتر پولارایزد رفلکشن داشتن تا اینکه مثلا این برگ گلها. از جهت ماها که داریم به گل و برگ و اینو نگاه میکنیم به نظر میاد که رفلکشن لایت از اونا پولاریزیشنش فرق میکنه. ولی سوال شما خیلی عمیق‌تر از این مسئله هست که آیا خود پلانت وقتی که نور رو میگیره آیا برای پلانت پولاریزیشن مهم هست یا نه؟ خیلی سوال عالیه و من جوابشو نمیدونم، ولی حتما سعی میکنم برام پیدا کنم و اگه پیدا کردم حتما براتون می‌نویسم.
متشکرم از لطفت.
خیلی ممنون دکتر. اتفاقا سوال بعدی هم که تو چت هست تقریبا تو همین زمینه است که میگه که البته حالا من فکر میکنم تو این زمینه است. گفته thanks a lot for informative presentation. Do you have any research about effect of polarization light on photosynthesis in green plants؟ این فکر کنم شبیه سوال آقای مهندس همین.
شبیه همین سوال هست. هر دو سوالا خیلی عالی هستش. منم خیلی کنجکاو شدم باید برم پیدا کنم ببینم واقعا هست یا نه. ان شاء الله
سخنرانی بعدی آقای دکتر در این زمینه. آقای مهندس نصرتی دستتون بالا، صداتون هم بسته است، بفرمایید.
قربان من سوال دیگه این هست که what about these polarized glasses که تو بازار هست یا توش گذاشتن های polarized و اون بر این مکانیزم کار میکنه، اگه نه چه جوری هست و آیا اون عینک‌های سه‌بعدی هم تو این زمینه‌ان یا اصلا داستان دیگه‌ای دارن؟
خیلی جالبه. خیلی ممنون از سوالتون. همه سوالا عالیه، خیلی جالبه. واقعا خوشحال میشم که با هم بحث میکنیم. Polaroid glasses, yeah, it's available in the market. I have one, you know. I mean, it's a very interesting, and it's relatively simple technology, by the way. Now, I mean, when it is very common. Now, how does that work? Now, there are certain, transparent structure like a glass with the Polaroid glasses that the way they work. Imagine that, for example, I get a glass. And imagine I have this material on it, which sometimes the polymers that they have there, but they design it such that when you send the light, if the polarization of the light, let's say, is in this direction, for example, it would not go through, but if it is in this direction, it would go through, for example. Yes, and that's relatively, easy way to make, and this technology is very mature, you know, several decades.
Kind of filtration actually, یعنی اون ویوا رو فیلتر میکنه تقریبا.
متوجه نشدم چی گفتی.
منظورم بود که در واقع اون بعضی از ویوا رو سلکشنی فیلتر میکنه.
درسته، ولی وقتی فیلتر میکنه معمولا هم توی ویزیبل دومین هستن که برای چشم بستگی به پولاریزیشن داره. اگه پولاریزیشن ورتیکال باشه یا هوریزونتال باشه، یک از اونها رو فیلتر میکنه. You can see it, the other one you cannot see. ولی در چرا این اصلا اختراع شده؟ در چه شرایطی میشه استفاده کرد؟ اون خیلی جالبه. یکی از دلایلی که پولاروید گلاسز در واقع اختراع شد، یکی از اپلیکیشناش برای چیز هست. فرض کنید شما میرید ماهیگیری. شما میرید بغل لیک برای که ماهی بگیرید. خب سطح آب سطح نسبتاً صافی هست. خورشید اون بالا هست و این خورشید نورش میاد میخوره به سطح آب و reflects back a lot. We call it glare. همه ما امتحان کردیم glare وقتی روز sunny day you go out you see that. Now, if you go there to do fishing, what is your goal? You would like to be able to actually see the fish in the water. Okay? The problem is that the light that's coming from the sun, and the light that's coming from the sun, by the way, is not polarized. In other words, that orientation of the electric field I mentioned to you is all directions. Okay, so it's combination of all the polarization. Now, it turns out that when a light actually hits a surface between two media, let's say air and water, the reflected light that you get, the amount of reflection that you get depends on the polarization. That's the nature of the surface. Has nothing to do with the Polaroid glasses, just nature. So if the light that's coming from the sun, the part of it that is horizontally polarized reflects more from the surface, the one that's vertically polarized reflect less. Now, so where does the rest of the light go? The rest of it goes into the water, naturally. Okay, so if you are sitting near a lake and the sun is there and reflects back from the water and comes to you, that's a big glare. Well, we know that this glare that's coming, good portion of that is horizontally polarized because it reflects more from the surface. The one that's vertical also reflects to us, but it's less because good portion of that go inside. Okay, so you're saying I'm sitting near the lake, but this reflection is really bothering me. How do I get rid of it? Well, if I don't look at it at all, well, of course, I don't see anything. But I want to see something in the water, but at the same time, I don't want to see the reflection from the surface. So here comes the invention of Polaroid glasses. The glass that you have is made such that the horizontal polarization will be blocked, but the vertical polarization will go through.
Ali, what about the 3D ones, 3D glass?
I will get to that, yeah. So this one would go and the other one does not go. So as a result, the major reflection that's coming from the water is eliminated. So the glare disappears. And the other polarization that goes into the water with the hit the fish and coming out, you can see it very nicely. So not only you get rid of the glare, or not completely, but most part of it, you actually also see the fish inside the water. So that's one application of that. Same thing for when you go skiing. Same thing when you are driving in a sunny day. When you are driving in a sunny day and there's another car in front of you, there's a big glare of the sunlight from the back windshield of the car. And that would prevent you to see the car in front of your car, our car. So if you use the Polaroid glasses, it cuts down that glare, so you can actually see the car that is in front of you, through the glass that you would see. Now, coming back to the 3D. 3D actually is quite interesting. There are different ways of generating the 3D vision. But first, let's ask this question. How do our eyes actually see 3D? I mean, everyday life, obviously we see the world 3D. And the reason we can see 3D because we have two eyes that are not in the same location. We have two eyes that there is some distance between them. So, it's very easy to check. If you clip one of your eyes and you see at the scene, and you close the other one, you see at the scene, you don't see exactly the same thing because our eyes would see with a certain angle. Our brain evolves since childhood when we are born, that when we see these two images from our two eyes that are slightly different angle, we develop the 3D perception of that. Now, of course, if we have only one eye and looking at that, we lose that 3D perception. But if we have it and then we lose one of the eyes, then our brain can adjust and can actually, again, gain that 3D. So the problem is if you like to create an image that is 3D, what usually they do is that, let's say in the Hollywood movies and so on, they use two cameras. And they take the image of the same scene with the two cameras that are located at two different locations, kind of like our eyes. They record these images, and then they will play it. And when they play it, you put a glass that the right eye would only see the image coming from camera 1, and the left eye would see the image that's coming from camera 2. In that case, you would actually see the 3D. Now, the question is, what kind of technology we should use that this one only see the image from camera 1 and the other one see the image from camera 2? There are different techniques. One technique is to use different color. So this will pick up one color, the other one would be another color. Another one is to do polarization. In other words, the image that's coming from camera 1, they put it vertical polarization. The one that's coming from the horizontal polarization, you put glasses that this will pick up this polarization, that the other polarization. So our brain cannot detect polarization because it's already filtered through here. Our eyes thinks that there are actually two images coming to our eyes, and our brain would actually interpret that as 3D. Yeah.
Excellent. خیلی ممنون.
مرسی دکتر، متشکرم. آقای سینا، صداتون بسته است، دستتون بالاست، بفرمایید.
سلام علیکم.
سلام علیکم.
سلام عرض می‌کنم خدمت همه دوستان، همینطور گردانندگان این جلسه خیلی خوب، و سلام ویژه خدمت دوست عزیز قدیمی آقای پروفسور نادرخان انقطاع. نادر جان، سینا زنوزی هستم.
میدونم، خیلی خوشحال شدم.
بله، من خیلی ممنونم از شما واقعا برای این جلسه خیلی خیلی عالی. یکی دو تا سوال البته ابتدایی و خیلی در واقع شاید پیش پا افتاده به نظر برسه خواهم داشت. قبل از اون نادر جان میخواستم سوالی بکنم. ما برای به اصطلاح 50مین سال ورود به دانشکده فنی که با جناب عالی افتخار داشتیم که در یک زمان وارد شدیم و هم دانشکده شدیم، در فکر با بچه‌های 52 ورود 52 در فکر تدارک یک سری برنامه‌های تقریبا در گلوبال همه جای دنیا هستیم. از جمله خب داریم به کمیته درست میکنیم. من اینجا در ونکوور هستم، بعد با بعضی دوستان که در ایران هستن یا در تورنتو در آمریکا لس آنجلس و اینها میخواییم که یه برنامه‌هایی را بندازیم. به هر حال خوشحال میشیم که بتونیم از وجود شما هم در بخشی حتما بهره مند بشیم و استفاده کنیم. حالا در اون رابطه من بعداً با جناب عالی تماس میگیرم، با هم صحبت میکنم. سوالی که من الان دارم یه سوال خیلی ساده است که غیر از این موارد استفاده کاربردی عملی که این به اصطلاح رشته در حالا دوربین ها و عینک و چیزای دیگه داره، آیا کاربردهای عملیش در زندگی روزمره چه موارد دیگری هستن؟ این یک سوال. سوال دیگه، آیا این بخش از در واقع علم در کیهان شناسی و فیزیک نجومی و ستاره شناسی هم آیا میتونه کاربرد داشته باشه یا نه؟ این سوال من.
خیلی ممنون. خیلی خوشحال شدم سینا جان. ما تماس بگیریم از طریق ایمیل در
حتما باهاتون تماس میگیرم نادر جان. ممنون.
نگردیم به سوال شما، هر دو سوال عالی. بدون سوال دوم اول جواب بدم. در واقع سوال دوم شما شبیه سوالی بود که قبلا یکی از دوستان عزیز در اینجا کردن. آیا این سوال میتونه در مورد نورهایی که در فضا هست
به نوعی؟
دقیقاً. The answer is yes. Actually it's has a quite interesting possibility. حالا چرا؟ به خاطر اینکه یکی از مواردی که در نجوم به کار میبره که شما میخواین نوری که از گالاکسی های خیلی خیلی دور میاد در نظر بگیرین. شما دیدین همین جیمز وب تلسکوپ شاهکار کرده. واقعا اون جیمز وب تلسکوپ واقعا یکی از پرقدرت ترین اختراعات بشر هست که شما در واقع حدود چندین بیلیون سال نوری رو در اول یونیورس میبینید در اینجا. در نتیجه در اون موارد چون سیگنال ها خیلی 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 ضعیف هستن، شما هر تکنولوژی به کار ببرید که بتونید سیگنال ها رو از نویز خارج بکنید و بتونید تشخیص بدید، it's a great thing. Polarization can be one of them, definitely. James Webb Telescope, by the way, has very sophisticated detector system. برای اینکه باید این دیتکتور سیستم ها طوری هست که تو نویز خیلی خیلی کمی داشته باشن، بتونن چیز در نظر بگیرن. ولی همونطور که در جوابی که دیگه از دوستانمون گفتم امشب، در هر کیسی که نور به طور خاص سکاترینگ داشته باشه، وقتی یه چیز نور سکاترینگ پیدا کنه معمولاً ویزیبیلیتی میاد پایین، به خاطر که شما یه آبجکتی رو میخوای ببینی ولی محیط اطرافش ممکنه اینقدر سکاترینگ بکنه که باعث بشه اون آبجکت رو نبینی، برای که اون بقیه صحنه ممکنه بیشتر دیتکتور رو اکتیو بکنه. در نتیجه اگه پولاریزیشن استفاده بکنیم که اون بقیه صحنه تاریک‌تر بشه و اون شیئی که شما دنبالش هستید، در این صورت مثلا میتونه یه دونه گالاکسی باشه که دنبالش هستید، که اون رو بتونید در نظر بگیری بدون اینکه بقیه صحنه دیتکتور شما رو اکتیویت بکنه، حتما مفید خواهد بود. ببینید این یکی به نظر من یکی از دلایلی هست که بعضی از این انیمال اسپیشیز ها در نیچر توی آب به دست آوردن، بلکه تو آب سکاترینگ زیاده. ببینید چشم من ایوالو نشده اینکه پولاریزیشن سنسیتیو باشه، برای که انسان ها در تو آب نبودیم، ما بیرون هستیم، در نتیجه سکاترینگ در هوا کمتره، ولی تو آب سکاترینگ زیاد هست. در نتیجه این اسپیشیز مثل اکتوپوس، مثل some of the species, they can actually evolve over billions of years in order to have a system that they basically remove the clutter. They call it removing the clutter or lowering the clutter and picking up the image that we would like to see. So the answer to your question, yes, it could have a very interesting possibilities there. So عذر this is جواب سوال دوم. سوال اول شما چی بود؟
سوال اول در رابطه با کاربردهای عملی دیگر این در زندگی روزمره غیر از حالا دوربین و عینک و اینها، آیا چیزای دیگه هم پیش بینی میشه در آینده مثلا کاربردهای عملی داره؟
به احتمال خیلی زیاد. ببینید سینا جان، هر موقعی که ما در زندگی روزمره احتیاج داشته باشیم به ایمیجینگ، یعنی تصویر برداری، حالا البته تصویر برداری مثلا همین شما آیفونی که شما در دستت هست در نظر داشته باش، این میتونه خب کامرای خیلی سافیستیکیتدی داره ولی این کامراش پولاریزیشن ابیلیتی نداره. تصور کن اگه این پولاریزیشن ابیلیتی هم داشته باشه، در نتیجه میتونیم چیزای بیشتری رو در طبیعت ببینیم. آیا اون اپلیکیشنی خواهد داشت یا نه؟ به قول معروف وقتی یه چیزی اختراع بشه و نشون بده که یه همچین کیفیتی داره، اپلیکیشن هم میاد دنبالش. یعنی که وقتی ما اون سیستم رو داشته باشیم میتونیم پیدا کنیم که چه کارهایی میتونیم در این مورد بکنیم. مثلا بذار یه مثال دیگه بزنم که ربطی به پولاریزیشن نداره. مثلا تصویر برداری برای امواج مادون قرمز، امواج ویزیبل، اونایی که ما میبینیم که چشم ما میبینه، ولی امواج مادون قرمز ما نمیتونیم ببینیم. ولی خب دوربین هایی هست که in the past 100 years they have been seeing infrared signal. Now one can ask, what's a good thing about infrared signal imaging? Well, they can find the temperature of people. That's what actually happened during the coronavirus. Remember when we were to go every place, they had these things that they put it, and in your forehead, and they know what's the temperature of your body. Or so when some physical phenomena, is being, applied, and you make a gadget out of it, most likely the application will follow. Okay.
خیلی ممنون، مرسی. یه تایم چک می‌کنیم.
خیلی ممنونم. مرسی نادر جان، متشکرم.
مرسی از شما. ساعت 8:15 است. با توجه به زمان سوال آقای صمدی رو به عنوان آخرین سوال با اجازه آقای دکتر در نظر می‌گیریم. آقای مهندس نوروزی دستتون بالا، صداتون هم بسته است، بفرمایید.
ببخشید فرمودین آقای مهندس صمدی، من صحبت کنم؟
عرض کردم بعد از ایشون دیگه سوالی رو نمیپذیریم، شما بفرمایید.
بله، سلام خدمت همه دوستان. آقای دکتر انقطاع خیلی تشکر میکنم. بسیار شب مطبوعی و من واقعا دارم لذت میبرم از این همه اطلاعاتی که دارم به دست میارم و سوالات دوستانم یکی از یکی جالبتر، واقعا همه ارزنده است. منم 2 تا سوال خدمتتون دارم. یکیش خیلی کوتاه هست و اون این که آیا تحقیقاتی در جریان هستش که این سیستم پولاراایزد ایمیجینگ در علم پزشکی وارد بشه و جایگزینی برای آلتراساوند و سی تی اسکن و ام آر آی و اینجور چیزا بشه یا نه؟ سوال دیگرم هم این هستش که این کامرایی که شما میفرمایین واقعا یک کامرا هست یا یک کامپیوتر فیچر هست؟ چون اگر این بتونه بیلت این بشه تو کامپیوتر، میشه کامپیوتر پروگرام کرد که وقتی این تصویر پولارایز وارد کامپیوتر میشه، اون پروگرام اونو تفسیر اینترپرت کنه و برای انسان، برای ما توضیح بده که این تصویر چیه و داستان چیه. اگه ما خودمون نمیتونیم ببینیم، کامپیوتر به جای ما ببینه. متشکرم.
خواهش می‌کنم، خیلی ممنون از لطفتون، از سوالتون و من کاملا با شما موافقم. واقعا همه سوالا امشب عالی بود و خیلی ممنون که این موقعیت دست اومد که همه ما دور هم جمع شیم با هم صحبت بکنیم. در مورد سوال اول شما جواب است yes. In fact, as I mentioned, one of the postdoctoral researcher in my group, Professor David Gruev, who was a postdoc in my group and also another colleague, after he finished, his work in my group and he became a professor himself, he went to University of Illinois at Urbana-Champaign, a very, well-regarded and very highly ranked university in the U.S. And he actually applied this polarization imaging to medical imaging. That's exactly what you were suggesting. Yes, he did that particularly, by the way, in imaging of the brain. So yes, yeah, this is actually, he's using it very successfully, by the way. I'm very proud of him. I mean,
so hopefully it's coming into the market soon.
Hopefully, yeah, that's right. I mean, he knows more about that because that became actually part of his career and he did a beautiful job. on that. So yes, I mean, it is being used, by the way, at least in his group and also in the research levels, that they're looking, using this methodology, for imaging, medical imaging. With regard to your second question, another excellent question, yes, absolutely. In fact, the first time we built the camera many years ago, as you saw in my presentation, we did it kind of like manually first. In other words, we had the camera, and then we put a polarizer in front of it, and then we took the image and we recorded the image in the computer, and then we rotate the polarization, literally manually, the first one, and then we took an image, and then we basically processed the two images together. But later on, I mean, that was the first, several tries we had. Later on, we decided to automate that, exactly as what you said. So what we did is that we made the polarizer in front of it that electronically you can switch and then take the image, and the image would be processed. Then later on, we made it even more automated. So rather than having the polarizer outside, we decided to actually using microelectronic feature to actually implement the polarizer inside the camera, and of course after the lens, rather than before the lens, and do it automatically. Yes, right now actually is in that stage that this former postdoc in my group, and now he's a professor there. Yes, it's right now in his lab, that's completely automated to go there. Yes, absolutely.
ممنونم.
مرسی آقای دکتر. آقای مهندس صمدی بفرمایید.
Two questions. One is science and the other one engineering. The first one, doctor, is when we talk about the receptors that the human eye and the insects, you mentioned about the randomness of the cells that actually are the receptors. So I assume the sources are the same. The receptors are responsible for the reaction, which is seeing it in a polarized or not. So how sure we are about this randomness? Very good point.
خیلی ممنون آقای صمدی. چون ببین اول این سوال عذر میخوام، گفتین دو تا سوال دارین یه دونه.
این اولیش بود. حالا دومی سوالم کاملا اپلاید و انجینیرینگ. حالا این اولی رو من میخواستم ببینم که بیسس این ابزرویشن اور اکسپریمنت این رندومنس که ما صحبت میکنیم و آیا هیچ پترنی هست که ما ندیدیم هنوز یا نمیبینیم؟
خیلی سوال جالبی هست. ببینیم برگردیم به این سلایدی که من بهتون نشون دادم که this anatomy of human eye. این رتینایی که در اینجا هست که it's a very sensitive surface of the eye, as I mentioned, millions of photoreceptors. So let me, if you see the cursor on my screen, the photoreceptors, which are rods or cones, are oriented radially. So these are all, going like this into the eye. Now, this is one of the example of that I'm showing over here. So that little rod, this end of it is the one that actually shows up on the surface of the retina. So when the light is coming from the lens, eventually gets over here. Unfortunately, this picture is vertical, but essentially you have to get this one and rotate it to become, surface of the retina. So when the lens is here, let's say, and the light is coming and gets to this and goes through this and come over here. Now, this section of the rod, we call it outer segment, consists of this disc, and I mentioned these are the molecules of visual pigments, and these are randomly oriented. Okay, so that's known, that's randomly oriented, so this cannot pick up any preferred polarization. So human eyes cannot detect polarization, so that's for that. Now, if your question is that is it possible that in some human eye this would not be randomly oriented? If that's your question, as far as I know, no. All the receptors in all of our eyes, these pigments are randomly oriented. But please remember that I'm just talking about these molecules being randomly oriented. These rods are all parallel with each other. So imagine that this is the back of the retina. I don't know whether I can see it in this. And then these rods are being, radially oriented into this. Now, inside the rod that you go, when you get to this point, these molecules of visual pigments are randomly oriented. So that cannot detect it. Now, But for some of the insects, and please let me clarify this, I'm not saying all the insects have this insect receptor, only some of them. You notice that these molecules are not randomly oriented, but they're anchored to the wall. And this anchoring to the wall is happen to be most of them, all of them parallel with each other. So when the light gets into the system, if the vibration of the electric field is parallel with these molecules, it gets more energy from the light than if the vibration is perpendicular to that. However, as I mentioned, and there was no time to go through some of the detail of that, in a sense, that by itself would be another interesting discussion. It turns out that in many of these insects that have this type of receptors, these receptors are not actually straight like this. They're actually rotated. So imagine that this structure, you make it kind of like a helix. Do it like that. So this anchoring to the wall also becomes a helical. Then in that case, it would lose the ability to detect the polarization of light. Then you might say, wait a second, why is it that this rod it has this anchoring, but then the nature has actually basically got rid of it by this helical aspect? The reason for that is because not all of these cells are being used for polarization. Only few of them are being used polarization because the insect can see other things too. So as a result, there is a diversity of this receptor there. Some of them can just see the intensity of light. Some of them can see the intensity and polarization. By combining this, the eyes would see both of them for that. So that's actually how these things actually behave there in some of the species, but not all of them. Usually vertebrates and primates, the eyes are like this, like a human eyes. So if you look at, cat's eye, if you look at dog's eyes, the structure of the eye is not that different from human eye. I mean, maybe smaller, but generally is one lens and the retina at the end. Whereas in the case of insect, it's very different. It is this is like 1,000 of this ommatidium, each one of them, and each one of them gets, one data point. So, for example, human eye has millions of these photoreceptors. So our eyes have a very high resolution. When you're looking at the screen, you see a lot of detail of the screen. Whereas, for example, let's say bees or ants, the resolution is very poor. It's just about, 15,000 points. That's it. So they don't have as much high resolution as we have in our eyes. And that's just because of the imaging system our eyes has. Is one lens and bring the image on the retina quite nicely. I hope I was able to answer your question.
Oh, thank you so much, Doctor. That was good. And the second question I had was applied on engineering. We used to use the polar light to actually to figure out the composition of minerals. That if we take a small sample of a rock and brush it enough and make polarized light to that, at some point they show different colors, and at some point it turns black, meaning that there is no reflection. So using that, we could actually guesstimate the composition of the rock. This is, I'm talking about early 70s that I did this experiment. How can this development of the new technology help on identifying the composition of the rocks?
Excellent point. Yeah, but you're absolutely right. I mean, the different minerals, different crystals have actually different polarization properties. These are actually, in the terminology of optics, we call it uniaxial crystal, biaxial crystals, birefringent crystals, meaning that different polarization would have different index of refraction. So if you have a light going through the crystal with the, let's say, vertical polarization, you have a different velocity of propagation than when you have, horizontal one. So this is called birefringence. And as a result, polarization play a very important role, by the way, in crystal. You're absolutely right. I anticipate, by the way, that this imaging could be quite, relevant and useful there, because you can actually detect some of the aspects of that. But yes, polarization is a very crucial part, an important part in crystal and crystallography, and also in minerals, as we said. Absolutely.
Okay. Thank you so much, Doctor. Learned a lot and need some time to digest what I learned. Thank you.
مرسی آقای دکتر، سپاسگزارم. خسته نباشید. ما این سشن رو ضبط کردیم توی کانال مهندس و یوتیوب مهندس این بارگذاری میشه. حالا دوستان اگه خواستن بعد مراجعه کنن مجدد بهش. آقای محقق، ما در خدمت شما هستیم.
بله آقای پروفسور انقطاع، مایلم از طرف هیئت مدیره و هیئت امنای کانون مهندس بله عذر میخوام. آقای خضرایی صداتون رو ببندین لطفا. اوکی، بله خیلی خوب، عذر میخوام ازتون. مایلم از طرف هیئت مدیره و هیئت امنای کانون مهندس از پروفسور نادر انقطاع برای لطف و محبتی که به کانون مهندس داشتن دعوت ما رو قبول کردن صمیمانه و صمیمانه هم به سوالهای و همه سوالات با لطف و مهربانی پاسخ دادن. قدردانی کنم این امید برای ما وجود داره که در آینده نه چندان دور باز هم حضور حضرت عالی رو داشته باشیم و استفاده کنیم از این دانش، فرزانگی و فریختگی شما و اختراعات و اکتشافات جدیدی که خواهید داشت. از همکارانم آقای منصور خدابنده، منصور صبا و منصور فروزی و از همه شما عزیزانی که تا آخرین لحظه موندید و به سخنان پروفسور انقطاع گوش دادید هم قدردانی کنم. من میکروفون رو آزاد میکنم برای حضرت عالی اگر صحبت نهایی داریم بفرمایید.
خیلی ممنون. اولا خیلی متشکرم آقای مهندس معدل از لطف شما و از این امکانی که به من دادید با شما باشم و در ضمن از شما یه بار دیگه تشکر میکنم به خاطر مسئله‌ای که در مورد برادر من گفتین. واقعا لطف دارین، جاش خیلی خالیه در قلب من و همیشه من برادر نازنینم رو میس میکنم و همونجوری که شما گفتین خاطرات جالبی ما با هم داشتیم. همونطور که من گفتین که موقعی که برادرم میومد آمریکا واقعا یادم میاد اون روزگاری که با هم خیلی کار می‌کردیم تا برادرم بیاد. در حال خیلی متشکرم که یادی از برادر من کردین. در ضمن از دوست عزیزم افشین جان، مهندس افشین خدابنده، خیلی خیلی لطف کردی افشین جان که این امکان رو من دادی که دوباره با همه این دوستان در اینجا باشم. افشین و من برمیگردیم به دوران دبیرستان هدف و دانشکده فنی و دوستیمون دوستی خیلی دراز مدتی هست و امیدوارم که هر چه زودتر دوباره همدیگه رو ببینیم افشین جان in 3D rather than Zoom. خیلی سپاسگزارم و از همه شما دوستان عزیز از کانون مهندس در کانادا خیلی خیلی سپاسگزاری میکنم. تمام دوستان عزیز، چه دوستانی که از هدف من میشناسم، چه دوستانی که از دانشکده فنی میشناسم و چه دوستانی که آشنا شدیم با هم در مدت این دوتا دور همی که با هم داشتیم. خیلی سپاسگزارم و امیدوارم که هر چه زودتر دوباره همدیگه ببینیم. من در خدمت شما هستم، هر موقع که مایل باشیم میتونیم دوباره دور هم جمع بشیم و با هم صحبت بکنیم. خیلی سپاسگزارم.
مرسی آقای پروفسور، متشکرم. من با عزتون با کلام آخر شما ختم جلسه رو اعلام میکنم. شب خوبی داشته باشید. سپاسگزارم برای همه چیز.
خیلی خیلی ممنون. متشکرم.
ممنون. خیلی ممنون از همه، از آقای پروفسور انقطاع عزیز. قربان.